4.5 billion years ago, a swirling disk of gas and dust began collapsing around our young Sunday. Within that cosmic debris field, particles collided, fused, and gradually built something extraordinary, a molten sphere that would one day cradle oceans, mountains, and life itself. Earth's story spans timescales almost beyond human comprehension, eons measured in hundreds of millions of years, continents drifting across the globe like slow-motion puzzle pieces, and life forms evolving from single cells into creatures that walked, swam, flew, and eventually looked up at the stars wondering where they came from. Tonight, we're taking a journey through deep time, from the planet's violent birth in a cloud of superheated rock to the age of giant ferns, armored fish, and thunder lizards that shook the ground. No speculation, no mythology, just the remarkable facts preserved in stone, ice, and the chemistry of ancient minerals. The prehistoric Earth wasn't just a prelude to our world. It was a laboratory where the rules of life were written, tested, and rewritten time and again. Before there was Earth, there was chaos. About 4.6 billion years ago, in a quiet region of the Milky Way galaxy, a massive cloud of gas and dust began to collapse under its own gravity. This wasn't a gentle process. Some astronomers believe a nearby supernova's shockwave may have triggered the collapse, sending ripples through the nebula that would become our solar system. As the cloud contracted, it started spinning faster, like a figure skater pulling in their arms, and most of the material fell toward the center, igniting nuclear fusion and giving birth to the sun. But not everything made it to the center. A rotating disk of leftover material, the protoplanetary disk, swirled around the infant star, and within that disk, the raw ingredients for planets waited. The protoplanetary disk was a violent place. Temperatures near the young sun reached thousands of degrees, vaporizing anything but the most heat-resistant materials. Farther out, where Earth would eventually form, conditions were cooler, but still far from calm. Microscopic dust grains drifted through the disk, occasionally bumping into one another. Some collisions caused the particles to bounce apart, but others, influenced by static electricity and molecular forces, caused them to stick together. Over thousands of years, these tiny aggregations grew into pebbles, then boulders, then objects kilometers across called planetesimals. The process accelerated as larger bodies exerted stronger gravitational pull, sweeping up material in their orbital paths like cosmic vacuum cleaners. Within a few million years, perhaps 10 million at most, the inner solar system contained dozens of planetary embryos, rocky bodies ranging from moon-sized to Mars-sized, each traveling its own elliptical orbit around the sun. These weren't the orderly, well-spaced planets we know today. Their orbits intersected and overlapped, making collisions not just possible, but inevitable. Computer simulations run by planetary scientists suggest that the inner solar system went through a period of giant impacts, where these embryos smashed into one another with unimaginable force. Each collision either shattered both bodies into fragments or, more often, resulted in a merger, two embryos becoming one larger protoplanet. The violence of these impacts generated enough heat to melt rock completely, creating vast oceans of molten magma on the surfaces of the growing planets. Earth emerged from this chaotic dance of collisions. Geochemical analysis of Earth's oldest minerals in comparison with meteorites, which are essentially unchanged samples of the early solar system, tells us that our planet accreted relatively quickly, reaching most of its current mass within 50 to 100 million years of the solar system's formation. The young Earth was nothing like the blue marble we know today. Its surface was an ocean of liquid rock, heated both by the constant bombardment of impacting debris and by the decay of radioactive elements trapped within the planet's interior. The atmosphere, if it could be called that, consisted of vaporized rock, carbon dioxide, nitrogen, and water vapor released from the planet's interior through countless volcanic eruptions. There was no oxygen, no continents, no oceans of liquid water, just a hellish world of red-hot magma beneath clouds of steam and toxic gases. During this violent accretion phase, something crucial was happening deep inside the growing planet. As Earth's mass increased, gravitational compression heated the interior to even higher temperatures. Heavier elements, particularly iron and nickel, began sinking toward the center, while lighter silicate minerals floated upward. This process, called differentiation, created Earth's layered structure, a dense metallic core surrounded by a thick mantle of hot silicate rock, topped by a thin crust. The differentiation process released enormous amounts of gravitational energy. Essentially, the potential energy of elevated iron was converted to heat as it fell toward the center, which kept the interior molten and drove the powerful convection currents that would later power plate tectonics. The formation of Earth's iron core would prove essential for life billions of years later, as the core's circulation would generate the magnetic field that shields our planet from lethal solar radiation. But Earth wasn't finished being shaped by catastrophe. Around 4.5 billion years ago, roughly 50 to 100 million years after the solar system's formation, the young Earth experienced the most dramatic event in its history, a collision so violent it would permanently alter the planet's structure and give us our unusually large moon. Scientists call it the giant impact, or sometimes the big whack, and the evidence for this cataclysm is written in the very rocks beneath our feet and in the samples of lunar soil brought back by Apollo astronauts. The impactor, which planetary scientists have nicknamed Theia after the Greek titan who gave birth to the moon goddess Selene, was roughly the size of Mars, about half Earth's diameter, and perhaps one-tenth its mass. Computer models suggest Theia formed in a gravitationally stable point along Earth's orbit, either leading or trailing our planet by about 60 degrees, a configuration called the Lagrange point. For millions of years, Theia grew by accreting material in this relatively safe position. But orbital dynamics are never perfectly stable over geological timescales. Eventually, gravitational perturbations from Jupiter and other planets nudged Theia out of its stable orbit, setting it on a collision course with Earth. When Theia struck Earth, the impact occurred at an oblique angle rather than head-on, with a relative velocity of perhaps 10 to 15 kilometers per second, about 40 times the speed of sound. The energy released was equivalent to billions of nuclear weapons detonating simultaneously. In an instant, Theia's iron core merged with Earth's core, adding to our planet's mass and explaining some puzzling features of Earth's composition. The mantles of both planets, the thick layers of rock surrounding their cores, were vaporized and ejected into space as a superheated plume of rock vapor that extended tens of thousands of kilometers from Earth's surface. Most of this material either escaped into space entirely or fell back to Earth, but a significant portion remained in orbit, forming a ring of molten debris around the planet. Over the following months and years, this ring of debris gradually coalesced into the moon. The process was surprisingly quick by geological standards. Most models suggest the moon reached its basic form within a year to a century after the impact. The newborn moon orbited much closer to Earth than it does today, perhaps only 15,000 to 20,000 kilometers away, compared to its current distance of about 384,000 kilometers. At that distance, the moon would have appeared 15 times larger in Earth's sky, creating tides hundreds of meters high in the magma ocean that covered Earth's surface. The moon has been slowly drifting away from Earth ever since, stealing rotational energy from our planet through tidal interactions, a process that continues today at a rate of about 3.8 centimeters per year, precisely measured by bouncing laser beams off reflectors left on the lunar surface by Apollo astronauts. The giant impact left Earth spinning much faster than it does now. Calculations based on the moon's orbital dynamics suggest that immediately after the impact, an Earth day lasted only about 5 hours. The planet was also tilted on its axis. The impact imparted angular momentum that gave Earth its current axial tilt of 23.5 degrees, the tilt responsible for our seasons. Without this tilt, Earth's climate would be far more uniform but also far less dynamic, potentially affecting the evolution of life billions of years later. The moon's formation had another crucial long-term consequence. It stabilized Earth's axial tilt. Planets without large moons, like Mars, experience wild variations in their axial tilt over millions of years, creating chaotic climate swings. Earth's moon acts as a gravitational anchor, keeping our planet's tilt relatively stable and our climate more predictable over geological timescales. After the giant impact, Earth entered what geologists call the Hadean Aeon, named after Hades, the Greek underworld, because conditions were quite literally hellish. The Hadean lasted from Earth's formation 4.6 billion years ago until about 4 billion years ago. though some geologists ended at 3.8 billion years ago. For most of the Hadean, Earth's surface remained molten or semi-molten. The energy from the giant impact alone would have taken millions of years to radiate away into space, keeping the entire planet's surface as a magma ocean hundreds of kilometers deep. Heavier minerals sank in this ocean while lighter ones floated, beginning the process of forming Earth's first primitive crust. We have remarkably little direct evidence from the Hadean Eon because plate tectonics, the recycling of Earth's crust, has destroyed almost all rocks from this time. The oldest known intact rock formation on Earth's surface is the Acasta gneiss in northwestern Canada, dated to about 4.03 billion years ago, right at the end of the Hadean. However, we do have a few tiny crystals of the mineral zircon that formed during the Hadean and survived to the present day. These zircons, found in younger rocks in Western Australia's Jack Hills, have been dated using uranium lead radiometric techniques to as old as 4.4 billion years. Their crystal structure and chemical composition tell a fascinating and somewhat controversial story. The Jack Hills zircons contain oxygen isotopes, variants of oxygen atoms with different numbers of neutrons, that suggest something unexpected about the Hadean Earth. When these zircons crystallized 4.4 billion years ago, the ratios of oxygen 18 to oxygen 16 trapped within them indicate they formed in the presence of liquid water. This is remarkable because it suggests that parts of Earth's surface had cooled enough for water to exist in liquid form far earlier than scientists previously believed. The conventional view held that Earth remained entirely molten for the first several hundred million years of its existence, but these tiny crystals hint that at least some solid crust and possibly even oceans existed as early as 4.4 billion years ago, a mere 160 million years after Earth's formation. This doesn't mean the Hadean was a pleasant place. Even if liquid water existed on the surface, the environment remained extraordinarily hostile. Volcanic activity was far more intense than anything seen in Earth's recorded history, with massive lava flows constantly resurfacing portions of the planet. The atmosphere was thick with carbon dioxide, water vapor, nitrogen, sulfur dioxide, and other volcanic gases, creating a greenhouse effect that kept surface temperatures much higher than today. There was no ozone layer to shield the surface from the sun's ultraviolet radiation, which would have been lethal to any complex organic molecules trying to form. The young sun itself was about 30% dimmer than it is today, yet the greenhouse atmosphere kept Earth warm enough for liquid water, solving what astronomers call the faint young sun paradox. Around 4.1 to 3.8 billion years ago, Earth and the other inner planets experienced what scientists call the Late Heavy Bombardment, sometimes abbreviated as LHB. This was a period of intense asteroid and cometary impacts, far more severe than the background bombardment rate during the rest of the Hadean. The evidence for the Late Heavy Bombardment comes primarily from the Moon, whose ancient crater highlands preserve a record of impacts that would have been erased on Earth by geological activity. By dating lunar samples brought back by Apollo missions, scientists determined that a disproportionately large number of impact craters formed during this relatively narrow window of time. What caused this sudden spike in bombardment rates remains debated. The leading explanation, called the Gneiss model, named after the French city where it was developed, not because it's pleasant, proposes that the giant planets Jupiter, Saturn, Uranus, and Neptune didn't form in their current orbits. Instead, they migrated inward and outward during the solar system's first several hundred million years, destabilizing the orbits of countless asteroids and comets in the outer solar system. When Jupiter and Saturn reached a particular orbital resonance around 4.1 billion years ago, they scattered these small bodies throughout the solar system, sending many of them careening toward the inner planets. An alternative hypothesis suggests the Late Heavy Bombardment represents not a spike, but simply the tail end of the initial planetary accretion phase, with crater dating giving a false impression of a distinct bombardment period. Regardless of its cause, the Late Heavy Bombardment had profound implications for Earth. The largest impacts would have vaporized any oceans that had formed, sterilizing the surface and resetting the conditions for life's emergence. Some scientists argue this bombardment delayed the origin of life on Earth, while others suggest that early life might have emerged multiple times, only to be wiped out by giant impacts before finally taking permanent hold after the bombardment subsided. The impactors themselves, particularly comets from the outer solar system, may have delivered significant amounts of water and organic molecules to Earth's surface. While Earth's water probably came primarily from water-rich asteroids incorporated during the planet's initial formation, cometary impacts during the late heavy bombardment could have supplemented Earth's water inventory. By about 3.8 billion years ago, the late heavy bombardment had ended, and Earth was finally approaching something resembling stable conditions. The surface had cooled enough that solid crust covered most of the planet, though it was likely much thinner and more fragmented than modern continental crust. Liquid water oceans existed, possibly covering most or all of the planet's surface, with volcanic islands rising from the depths to form the first patches of dry land. The atmosphere remained rich in carbon dioxide and nitrogen, but it lost much of its water vapor as the surface cooled and the oceans condensed. The planet's iron core had fully differentiated and begun generating a magnetic field through the dynamo effect, convecting liquid metal acting like a natural electrical generator, providing crucial protection against the solar wind that would otherwise strip away the atmosphere. Earth had survived its violent birth. The next chapter in its story would be even more remarkable. Somehow in those ancient oceans beneath a toxic sky, chemistry would cross the threshold into biology and life would begin. As the Hadean Eon drew to a close around 4 billion years ago, Earth was transforming from a molten hell into something almost recognizable, a world with solid ground, liquid oceans, and an atmosphere capable of retaining heat. The transition wasn't sudden or uniform. Different regions of the planet cooled at different rates, and the process took hundreds of millions of years. But by examining the chemistry of ancient zircon crystals, the composition of Earth's oldest rocks, and comparing our planet to other bodies in the solar system, scientists have pieced together how Earth acquired the two features that would prove essential for life: a stable ocean and a protective atmosphere. Water is so abundant on Earth today, covering 71% of the surface to an average depth of 3,700 meters, that we sometimes forget how remarkable its presence is. Venus, our closest planetary neighbor in size and composition, has almost no water. Mars lost most of its water billions of years ago. So where did Earth's water come from, and when did it arrive? For decades, scientists debated whether Earth's water was delivered by comets smashing into the planet after it had cooled, or whether water was present from the beginning, incorporated into the rocky material that built the planet. Recent evidence strongly supports the latter explanation. Meteorites called carbonaceous chondrites, which represent some of the most primitive, unchanged material from the early solar system, contain significant amounts of water, up to 20% by weight, chemically bound within their minerals. When these water-rich asteroids collided and merged during Earth's formation, their water came along for the ride. The hydrogen in Earth's oceans has a distinctive isotopic signature, a specific ratio of ordinary hydrogen to deuterium, a heavier form with an extra neutron, that closely matches carbonaceous chondrites but differs from most comets. This chemical fingerprint tells us that the bulk of Earth's water likely came from asteroids during the planet's initial accretion, not from later cometary impacts, though comets probably contributed some fraction of our water. But having water trapped in minerals deep underground is very different from having liquid oceans on the surface. For water to exist as a liquid, temperatures must be within a relatively narrow range, above 0 degrees Celsius but below 100 degrees at Earth's surface pressure. During the Hadean Eon, as Earth's surface gradually cooled, the planet reached a critical threshold. Water vapor that had been released from the interior through volcanic eruptions, filling the atmosphere as steam, began to condense. Rain fell for the first time, though it would have evaporated before reaching the ground initially, as the surface remained too hot. As cooling continued, the rain finally reached the surface as liquid, collecting in the lowest areas to form the first puddles, then lakes, and eventually vast oceans. The timing of this ocean formation remains uncertain. The oxygen isotopes in 4.4 billion-year-old zircons suggest liquid water existed that early, but some scientists argue these zircons could have formed in magma that merely contained water-rich minerals, not necessarily in the presence of surface oceans. A more conservative estimate places the formation of stable, long-lasting oceans around 4.2 to 4.0 billion years ago. What seems certain is that by 3.8 billion years ago, when the late heavy bombardment was ending, Earth had substantial oceans, possibly global in extent. Evidence for this comes from rare sedimentary rocks of that age, which could only have formed through the action of water weathering and depositing minerals. These first oceans would have been acidic and mineral-rich, nothing like the seas we know today. Rivers, if they existed, which requires raised land masses, would have eroded volcanic rocks, carrying dissolved minerals into the ocean. Underwater volcanic vents would have poured additional minerals and metals into the water, along with dissolved gases from Earth's interior. The ocean's chemistry was dominated by iron, magnesium, calcium, and other metals, while the water's pH was likely acidic due to high concentrations of dissolved carbon dioxide from the atmosphere. Chlorine gas from volcanic eruptions dissolved in seawater, gradually making the ocean salty, though they may not have been as salty initially as they are today. The early oceans were also much warmer than today's seas. Surface temperatures probably ranged from 50 to 85 degrees Celsius, too hot for humans to swim in comfortably, but well within the range tolerated by modern extremophile microorganisms that live in hot springs. Some scientists have argued for even hotter oceans, possibly exceeding 100 degrees Celsius, kept liquid by the immense pressure of a thick carbon dioxide atmosphere. The debate continues, but what's clear is that these hot, mineral-rich, chemically active oceans will provide the perfect environment for the complex chemistry that would eventually lead to life. While the oceans were condensing, Earth was simultaneously building its atmosphere through a process called outgassing. Every time a volcano erupted, and during the late Hadean and early Archean eons, volcanic activity was far more intense than anything witnessed in human history. It released gases trapped within Earth's interior. These gases bubbled up from the mantle, escaped through fractures in the crust, and accumulated above the surface. Over hundreds of millions of years, this relentless outgassing built an atmosphere thick enough to trap heat and shield the surface from the harshness of space. The composition of this early atmosphere was fundamentally different from the air we breathe today. Volcanic gases on modern Earth consist primarily of water vapor, carbon dioxide, and sulfur dioxide, with smaller amounts of nitrogen, hydrogen sulfide, carbon monoxide, and hydrogen. Scientists assume Earth's primordial atmosphere has similar composition, though direct evidence is impossible to obtain since gases don't fossilize. The dominant components were likely carbon dioxide and nitrogen, with substantial water vapor before the oceans fully condensed. Critically, there was essentially no free oxygen, a gas so reactive that it quickly combines with rocks, minerals, and other chemicals unless constantly replenished by life. This oxygen-free atmosphere would have been immediately lethal to modern humans and most contemporary life forms, but it had its advantages for a young planet trying to establish stable conditions. Carbon dioxide, though toxic to us in high concentrations, is an extremely effective greenhouse gas. It traps infrared radiation, heat, that Earth's surface radiates back towards space, keeping that energy in the atmosphere and warming the planet. This greenhouse effect was crucial during Earth's early history because the young sun was significantly dimmer than it is today, producing only about 70% of its current energy output. Without a thick carbon dioxide atmosphere, Earth should have frozen solid. Instead, the greenhouse effect kept temperatures warm enough for liquid water, solving what astronomers call the faint young sun paradox. Calculations suggest Earth's early atmosphere may have contained 100 to 1,000 times as much carbon dioxide as today's atmosphere, creating a surface pressure perhaps 2 to 10 times higher than the present 1 bar at sea level. Living under such conditions would feel like being underwater at moderate depth. The increased pressure would be noticeable, but not crushing. The thick atmosphere would have scattered light differently, possibly giving the sky a different color, perhaps orange or reddish rather than blue, though this remains speculative. Visibility might have been limited by the haze of volcanic aerosols constantly suspended in the air. Nitrogen, the gas that makes up 78% of today's atmosphere, was probably present from the beginning, though in what concentration remains uncertain. Unlike carbon dioxide, which dissolves readily in water and can be locked into carbonate rocks like limestone, nitrogen is relatively inert. It doesn't easily react with other chemicals or dissolve in water, so once volcanic outgassing released it into the atmosphere, it tended to stay there. Over geological time, as carbon dioxide gradually got removed from the atmosphere through weathering and ocean chemistry, nitrogen's relative percentage increased, eventually becoming the dominant atmospheric gas even though the total atmospheric pressure decreased. One component conspicuously absent from the early atmosphere was ozone. Today, a layer of ozone, a molecule consisting of 3 oxygen atoms bonded together, exists in the stratosphere about 15 to 35 kilometers above Earth's surface. This ozone layer absorbs most of the sun's harmful ultraviolet radiation, protecting life on the surface from DNA-damaging UV rays. But ozone requires oxygen to form, and the early Earth had no free oxygen. This meant that ultraviolet radiation bathed the surface and penetrated the upper layers of the ocean with an intensity far greater than anything experienced today. This UV radiation would have been destructive to complex organic molecules, but also provided energy that could drive chemical reactions, potentially helping to synthesize the building blocks of life. The early atmosphere also lacked a strong protective magnetic field connection initially, though this changed as Earth's core fully differentiated and the dynamo effect kicked in. Earth's magnetic field doesn't actually shield the surface from much, it's far too weak for that, but it plays a crucial role in protecting the atmosphere itself. The solar wind, a stream of charged particles constantly flowing from the sun, can strip away atmospheric gases from planets that lack magnetic fields. Mars, which lost its global magnetic field early in its history, gradually lost most of its atmosphere to solar wind erosion over billions of years. Earth's magnetic field deflects most of these charged particles, creating the magnetosphere, a bubble of magnetic influence extending tens of thousands of kilometers into space. Without this protection, Earth might have suffered the same fate as Mars, losing its oceans and atmosphere to space. Evidence for Earth's early magnetic field comes from ancient rocks containing magnetic minerals that aligned with Earth's field when they solidified. The oldest such evidence dates to about 3.5 billion years ago, though the magnetic field almost certainly existed earlier. The strength of the ancient magnetic field appears to have varied considerably, sometimes weakening to half its current strength or even temporarily reversing polarity, with north and south magnetic poles swapping positions. These fluctuations suggest that the dynamics of the liquid iron core were still stabilizing, but the crucial protective effect was in place. The interaction between Earth's new ocean and its carbon dioxide-rich atmosphere created the planet's first major chemical cycle, one that would eventually regulate global temperature for billions of years. When carbon dioxide dissolves in water, it forms carbonic acid, making the ocean slightly acidic. This acidic water then reacts with rocks on the seafloor, particularly basaltic rocks rich in calcium, magnesium, and iron. The chemical weathering process pulls carbon dioxide out of the atmosphere, locks it into carbonate minerals, and releases other elements into the water. Over millions of years, this process could have removed enormous amounts of carbon dioxide from the atmosphere, gradually weakening the greenhouse effect and cooling the planet. But Earth didn't spiral into a frozen state because volcanic activity kept replenishing atmospheric carbon dioxide. Underwater volcanic vents and continental volcanoes constantly released fresh carbon dioxide from the mantle, where carbon had been trapped since Earth's formation. A balance emerged between removal through weathering and addition through volcanism. This carbon cycle represented Earth's first major feedback system, a self-regulating mechanism that kept temperatures within a habitable range despite external changes like the gradually brightening sunday. When temperatures rose, weathering accelerated, pulling more carbon dioxide from the atmosphere and cooling the planet. When temperatures dropped, weathering slowed while volcanic output continued, rebuilding the greenhouse effect. The early ocean wasn't uniform or stagnant. Temperature differences between the equator and poles, even on a much warmer Earth than today, would have driven circulation patterns. Deep ocean currents carried cold, dense water from higher latitudes toward the equator, while surface currents moved warm water poleward. These circulation patterns distributed heat around the planet and mixed nutrients throughout the ocean, a crucial service for the chemistry that would eventually generate life. Unlike modern oceans, which are oxygenated throughout and teem with life at all depths, the early ocean's deep waters were anoxic, meaning they contained no dissolved oxygen. Instead, these depths were rich in dissolved iron, manganese, and other metals that would immediately precipitate out of solution in the presence of oxygen. Hydrothermal vents played a particularly important role in the early ocean's chemistry and possibly in life's origins. These vents form where seawater seeps down through cracks in the ocean floor, gets heated by magma chambers or hot rock below, and then shoots back up at temperatures reaching 400 degrees Celsius or higher. The superheated water doesn't boil because of the immense pressure at depth. As this hot, acidic, mineral-laden water erupts from the seafloor, it mixes with the cold seawater, causing dissolved minerals to precipitate out and form chimney-like structures that can grow tens of meters tall. The chemical gradients at these vents, hot versus cold, acidic versus alkaline, reduced versus oxidized, provide energy that can drive chemical reactions without any input from sunlight. Modern hydrothermal vents support thriving ecosystems based on chemosynthetic bacteria that harvest energy from the chemical gradients rather than from photosynthesis. On the early Earth, before life existed, these same gradients could have driven the synthesis of increasingly complex organic molecules. A particular type of vent called an alkaline hydrothermal vent, which produces warm but not superheated water with a high pH, creates natural chemical reactors within its porous mineral walls. These microscopic chambers concentrate chemicals and catalyze reactions, acting almost like primitive cells. Some scientists argue these alkaline vents, rather than Darwin's famous warm little pond on the surface, were the most likely birthplace of life, though this remains debated. As the Archean Eon began around 4 billion years ago, Earth was settling into a new phase of relative stability after the chaos of the Hadean. The late heavy bombardment was ending, the oceans were established, and the atmosphere had reached a quasi-stable composition dominated by carbon dioxide and nitrogen. Volcanic islands rose above the ocean's surface, providing the first substantial dry land, though nothing like modern continents existed yet. The crust was thinner and more prone to melting and recycling than today's thick continental crust. Plate tectonics, the motion of large crustal plates driven by convection in the mantle, may have operated differently than it does today, perhaps with more numerous, smaller plates moving faster, or possibly with a different mechanism altogether involving vertical churning rather than horizontal sliding. The water cycle was also operating, though more vigorously than today due to higher temperatures. Water evaporated from the warm ocean surface, rose into the atmosphere, condensed into clouds, and fell as rain. This rainfall eroded the volcanic rocks on land, creating the first sediments, particles of weathered rock that rivers carried to the ocean and deposited in layers on the seafloor. These sediments, eventually compressed into sedimentary rocks, would preserve the geological record of Earth's history, including eventually the first traces of life. The cycle of evaporation, precipitation, and runoff also concentrated certain elements and minerals, creating deposits that would prove chemically interesting for the emergence of living systems. By 3.8 billion years ago, Earth possessed all the basic ingredients necessary for life: liquid water, a source of energy in the form of sunlight and chemical gradients, the right temperature range, a protective magnetic field, and a rich chemical environment with carbon, nitrogen, phosphorus, and trace metals dissolve in the ocean. The stage was set. Somewhere in those ancient seas, or perhaps in a sheltered pool on land, or most likely at a hydrothermal vent on the ocean floor, chemistry was about to cross an invisible threshold into biology. The origin of life on Earth remains one of science's most profound mysteries, not because we lack theories, but because we're trying to reconstruct events that happened billions of years ago and left almost no direct evidence behind. What we do know is that sometime between 4 billion and 3.5 billion years ago, during the Archean Eon, lifeless chemistry became living biology. Simple organic molecules somehow organized themselves into self-replicating systems capable of evolution, metabolism, and response to their environment. The transition happened at least once, possibly multiple times, and it transformed Earth forever. The Archean Eon stretched from about 4 billion years ago to 2.5 billion years ago, encompassing roughly 1.5 billion years, nearly a third of Earth's entire history. The planet during the early Archean looked dramatically different from today. Continents as we know them didn't exist. Instead, small volcanic islands and Protocontinents, fragments of thicker, more stable crust, dotted a global ocean. These early landmasses were composed primarily of basalt and komatiite, an ultramafic rock that forms from extremely hot magma and is rarely produced by modern volcanoes. The ocean remained hot by today's standards, perhaps 50 to 70 degrees Celsius at the surface, heated by the planet's still vigorous internal heat and a greenhouse atmosphere rich in carbon dioxide and methane. The sky would have appeared alien to modern eyes. Without oxygen, there was no blue color scattered by atmospheric gases. The thick atmosphere, laden with volcanic aerosols and greenhouse gases, might have given the sky an orange or pale yellow tint. The sun appeared dimmer than today, but still provided substantial energy to the surface. The moon loomed much larger, orbiting closer to Earth and creating massive tides that swept across the global ocean twice per day. A day lasted only about 18 hours during the early Archean, as Earth still spun faster than it does now. The combination of rapid rotation and the nearby moon created extreme tidal forces that may have been important for concentrating organic chemicals in tidal pools. When did life first appear? The oldest widely accepted evidence comes from stromatolites, layered rock structures formed by microbial mats, found in Western Australia's Pilbara region and dated to 3.48 billion years ago. Stromatolites form when communities of microorganisms, primarily cyanobacteria in modern examples, trap and bind sediment particles, creating thin layers that accumulate over time. The ancient stromatolites from Pilbara show the same characteristic wavy, layered structure as modern stromatolites, strongly suggesting they were created by microbial communities. However, some scientists argue these structures could have formed through non-biological processes, making the interpretation controversial. More definitive evidence comes from slightly younger rocks. Stromatolites from the Dresser Formation in Australia, dated to 3.48 billion years ago, contain organic carbon with an isotopic signature, specifically a ratio of carbon-12 to carbon-13, that matches what living organisms produce. Life preferentially uses the lighter carbon-12 isotope over carbon-13, leaving a chemical fingerprint in organic material. Additionally, researchers have found microscopic tubes and filaments in these rocks that resemble the shapes of simple bacteria, though proving these are actual microfossils rather than mineral artifacts remains challenging. Even older hints of life exist but remain highly controversial. Carbon particles trapped in 3.95 billion-year-old sedimentary rocks from Labrador, Canada, show isotopic ratios consistent with biological activity. If confirmed, this would push life's origin back to within a few hundred million years of the late heavy bombardment's end. Some scientists have claimed even earlier evidence, graphite particles in 4.1 billion-year-old zircons from Western Australia that might indicate life existed during the Hadean Eon. But these extraordinary claims face significant skepticism from the scientific community. The graphite could have contaminated the zircons later, or it could have formed through non-biological processes. What seems clear is that life appeared remarkably quickly once conditions permitted. If we accept the conservative estimate that life existed by 3.5 billion years ago, that's only about 300 to 500 million years after the late heavy bombardment ended and Earth became stably habitable. Given the complexity of even the simplest living cell, with its genetic material, metabolism, and membrane-bounded structure, the rapid appearance of life suggests either that life arises easily when conditions are right, or that many of the chemical steps toward life happened during the violent Hadean Eon and were merely preserved once bombardment ceased. The question of how life actually began, the specific chemical pathway from non-living molecules to living cells, has fascinated scientists since Darwin himself speculated about a warm little pond where the right combination of chemicals, energy, and time might have sparked life. Modern origin of life research has produced several competing but not mutually exclusive hypotheses, each addressing different aspects of the enormous puzzle. One fundamental challenge is defining what counts as life. Modern cells are astonishingly complex, containing thousands of different proteins, elaborate metabolic pathways, genetic material made of DNA, and sophisticated machinery for reading that genetic code and building proteins. Even the simplest free-living bacterium today, has hundreds of genes and requires hundreds of different molecules to function. Life clearly didn't spring into existence fully formed with all this complexity. Instead, there must have been simpler proto-life or pre-life that gradually evolved into cellular life as we know it. Most origin of life scenarios begin with organic molecules, compounds containing carbon chains and rings that form the building blocks of life. 4 types of organic molecules are particularly crucial: amino acids, which link together to form proteins; nucleotides, which link together to form DNA and RNA; lipids, which form cell membranes; and simple sugars, which provide energy and structural components. The question is whether these molecules could form spontaneously on the early Earth, or whether they needed to be delivered from space by meteorites and comets. The famous Miller-Urey experiment of 1953 demonstrated that organic molecules can form from simpler precursors under plausible early Earth conditions. Stanley Miller, then a graduate student working with Harold Urey at the University of Chicago, created a sealed apparatus containing water, methane, ammonia, and hydrogen, a mixture thought to resemble Earth's early atmosphere. He heated the water to produce vapor, passed the vapor through a chamber where electric sparks simulated lightning, then cooled the vapor back into liquid and collected it. After just 1 week, the water had turned pink. An analysis revealed it contained several amino acids, the building blocks of proteins. Subsequent experiments using different gas mixtures and energy sources have produced all the major types of biological molecules, demonstrating that prebiotic chemistry could have synthesized life's building blocks. However, the Miller-Urey experiment's assumed atmosphere composition has fallen out of favor. Most scientists now believe the early atmosphere contained primarily carbon dioxide and nitrogen rather than methane and ammonia, and these gases are less reactive, making organic synthesis more difficult though still possible. Additionally, meteorite analysis has shown that space itself is a factory for organic molecules. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, including many found in living organisms. Comets contain complex organic molecules formed in interstellar space. The early Earth was likely showered with organic molecules from space, supplementing whatever chemistry occurred on the planet's surface. Having building blocks is one thing. Assembling them into something that can replicate and evolve is another challenge entirely. Modern life uses DNA to store genetic information and proteins to perform most cellular functions, but DNA can't replicate without protein enzymes, and proteins can't be built without DNA instructions. This chicken and egg problem puzzled origin of life researchers for decades until the discovery that RNA, a molecule chemically similar to DNA, can both store genetic information and catalyze chemical reactions like a protein enzyme. This discovery led to the RNA world hypothesis, first articulated clearly by Harvard molecular biologist Walter Gilbert in 1986. The hypothesis proposes that early life used RNA for both genetic storage and catalysis, solving the chicken and egg problem. RNA molecules that could catalyze their own replication would have had a tremendous advantage, allowing them to multiply without needing other molecules. Over time, natural selection would have favored RNA sequences that replicated more accurately and efficiently. Eventually, this RNA-based life evolved the ability to synthesize proteins, which are better catalysts than RNA, and to use DNA, which is more stable than RNA for long-term information storage. Modern cells retain traces of this RNA world. Ribosomes, the cellular machines that build proteins, are made primarily of RNA, suggesting they are molecular fossils from an earlier era. The RNA world hypothesis is elegant but faces significant challenges. RNA is a complex molecule that's difficult to synthesize without enzymes. Researchers have managed to create RNA nucleotides under prebiotic conditions, but linking them into long chains remains problematic. Additionally, RNA is chemically unstable, especially in hot conditions like those on the early Earth. Some scientists propose even simpler precursors to RNA, while others suggest that metabolism, the chemical reactions that extract energy from the environment, emerge before genetic replication, with early life consisting of self-sustaining networks of chemical reactions rather than replicating molecules. Where did these crucial chemical reactions occur? Three main candidates have emerged. The first is Darwin's warm pool scenario, shallow ponds or lakes on volcanic islands that concentrate organic molecules through evaporation, with cycles of wetting and drying potentially helping to link building blocks into chains. The second is the deep ocean, specifically hydrothermal vents where hot, mineral-rich water erupts from the seafloor. These vents create chemical gradients and provide energy, minerals that act as catalysts, and microscopic chambers within porous mineral walls that could concentrate molecules. The third, more recent proposal is that life began in thin films on mineral surfaces, particularly on the face of certain clay minerals that can catalyze organic reactions and even help replicate RNA-like molecules. The most popular current hypothesis for life's birthplace focuses on alkaline hydrothermal vents, particularly a type discovered in 2000 called Lost City vents after a field found on the mid-Atlantic ridge. Unlike the superheated black smoker vents that spew water at 400 degrees Celsius, alkaline vents produce warm water around 40 to 90 degrees Celsius at a pH of 9 to 11. The temperature is compatible with organic chemistry, and the alkaline water creates a chemical gradient when it meets the acidic, iron-rich ocean. This gradient across the thin mineral walls of the vent structures can drive chemical reactions that produce organic molecules and even primitive metabolism. During the early stages of oxygenation, the main beneficiaries were bacteria that evolved cellular machinery to detoxify oxygen and eventually to harness it for energy production. The Great Oxygenation Event also triggered a climate catastrophe. Methane, which had been a significant component of the Archean atmosphere, is an extremely potent greenhouse gas, about 80 times more effective at trapping heat than carbon dioxide over a 20-year period. Methane was produced by methanogenic archaea living in oxygen-free sediments and was stable in the anoxic atmosphere. But when oxygen appeared, it reacted with atmospheric methane, breaking it down into carbon dioxide and water. Carbon dioxide is a much weaker greenhouse gas than methane. As the methane greenhouse collapsed, global temperatures plummeted, possibly triggering Earth's first major glaciation, the Huronian glaciation, named after rock formations north of Lake Huron in Canada. Evidence for this glaciation comes from glacial deposits called tillites, sedimentary rocks formed from the debris deposited by glaciers, found in rocks dating to 2.4 to 2.1 billion years ago. These deposits appear at latitudes suggesting glaciers extended nearly to the equator, implying a global or near-global freeze. Some scientists propose this was Earth's first snowball Earth event, where the entire planet became covered in ice. The glaciation may have lasted millions of years, with ice sheets kilometers thick covering both land and ocean. Eventually, volcanic carbon dioxide accumulated in the atmosphere despite the ice cover, rebuilding the greenhouse effect and melting the ice, but not before profoundly impacting the biosphere. The period following the initial Great Oxygenation Event, from about 2.3 to 1.8 billion years ago, saw continued changes in atmospheric composition. Oxygen levels probably fluctuated, rising and falling as the balance between oxygen production by cyanobacteria and oxygen consumption by chemical reactions shifted. The massive banded iron formations continued to form, with peak deposition occurring around 1.9 to 1.8 billion years ago, suggesting pulses of oxygen production or changes in ocean circulation that brought iron-rich deep water to the surface. Eventually, the ocean's dissolved iron was largely depleted, ending the formation of major banded iron formations and allowing oxygen to accumulate in seawater as well as in the atmosphere. The Proterozoic Eon, which began 2.5 billion years ago and lasted until 541 million years ago, encompassed this extended period of atmospheric and oceanic transformation. The Eon's name, derived from Greek words meaning earlier life, reflects the fact that life was diversifying and evolving during this immense span of time, even though visible fossils remained relatively rare. The early Proterozoic atmosphere probably contained only 1 to 10% of modern oxygen levels, enough to fundamentally change chemistry and climate, but not enough to support complex animal life, which requires higher concentrations. One fascinating aspect of the Great Oxygenation Event is the role of plate tectonics and continental evolution. During the Archean Eon, Earth's continental crust was relatively limited, consisting mainly of small volcanic islands and protocontinents. But during the late Archean and early Proterozoic, the volume of continental crust increased substantially as volcanic activity and tectonic processes built thicker, more stable landmasses. These growing continents weathered more extensively, consuming atmospheric carbon dioxide through the reaction of rainwater with silicate rocks. The burial of organic carbon, dead cyanobacteria, and other organisms in marine sediments also removed carbon from the active carbon cycle, further reducing greenhouse gases. This increase in continental weathering and organic carbon burial may have worked in concert with cyanobacterial oxygen production to trigger the Great Oxygenation Event. Some models suggest that oxygen levels remained low for hundreds of millions of years after. Cyanobacteria evolved because the continuous influx of volcanic and metamorphic gases consumed the oxygen as fast as it was produced. Only when continental weathering accelerated and reduced the flux of these oxygen-consuming gases did atmospheric oxygen begin to accumulate. This hypothesis links biological innovation with geological processes, showing how life and the physical Earth evolved together as an integrated system. The oxidation of Earth's surface also affected nutrient cycles crucial for life. Phosphorus, an essential element for DNA, RNA, and cell membranes, became more bioavailable in an oxygenated world. In anoxic conditions, phosphorus tends to stay bound in minerals and sediments, but oxidative weathering releases phosphorus into solution where organisms can use it. However, this increased phosphorus availability may have been partially offset by iron oxidation. Ferric iron compounds readily bind phosphorus, removing it from circulation. The complex interplay of these nutrient cycles influenced the productivity of marine ecosystems and the pace of evolutionary change. Another consequence of oxygenation was the formation of Earth's ozone layer. Ozone, a molecule consisting of 3 oxygen atoms bonded together, forms when ultraviolet radiation from the sun strikes oxygen molecules in the upper atmosphere. The accumulation of atmospheric oxygen during the Great Oxygenation Event led to ozone formation in the stratosphere, creating a shield against harmful UV radiation. Before the ozone layer existed, UV radiation penetrated Earth's surface with an intensity that would destroy most complex organic molecules and damage DNA. The ozone layer's formation made shallow waters and land surfaces much more hospitable to life, though it will be hundreds of millions of years before organisms fully exploited these newly protected environments. The Great Oxygenation Event also left its mark on the evolution of biochemistry. Organisms evolved sophisticated enzymes to manage oxygen's destructive potential. Catalase and superoxide dismutase, enzymes that break down reactive oxygen species, became essential for survival in oxygenated environments. The evolution of aerobic respiration, using oxygen as the final electron acceptor in metabolism, represented an enormous biochemical innovation that would power all complex life. The electron transport chains that modern eukaryotes use for respiration are variations on systems that first evolved in bacteria during the Proterozoic. By about 1.8 billion years ago, oxygen levels had stabilized to perhaps 1 to 10% of the atmosphere, and the ocean's surface waters had become oxygenated, though the deep ocean likely remained anoxic for hundreds of millions of years longer. The world had been transformed. Red beds, oxidized sedimentary rocks rich in ferric iron, became common in the geological record, replacing the gray and green rocks characteristic of the anoxic Archean. The stage was set for the next major transition in Earth's history, the evolution of complex cells with nuclei and specialized internal compartments, the eukaryotes that would eventually give rise to all animals, plants, and fungi. The Great Oxygenation Event stands as one of the most profound changes in Earth's history, comparable in significance to the origin of life itself. It was driven by biology, by the metabolic waste product of cyanobacteria, but it transformed geology, chemistry, and climate. It caused mass extinction among anaerobic organisms while opening new opportunities for aerobic life. It demonstrates how life doesn't simply adapt to its environment, but actively reshapes that environment in ways that feed back on evolution. Earth after oxygenation was a fundamentally different planet than Earth before, And the revolution begun by cyanobacteria 2.4 billion years ago continues to shape our world today as we breathe the oxygen-rich air they made possible. The Proterozoic Eon, which began 2.5 billion years ago and lasted until 541 million years ago, encompassed this extended period of atmospheric and oceanic transformation. The Eon's name, derived from Greek words meaning earlier life, reflects the fact that life was diversifying and evolving during this immense span of time, even though visible fossils remained relatively rare. The early Proterozoic atmosphere probably contained only 1 to 10% of modern oxygen levels, enough to fundamentally change chemistry and climate, but not enough to support complex animal life, which requires higher concentrations. One fascinating aspect of the Great Oxygenation Event is the role of plate tectonics and continental evolution. During the Archean Eon, Earth's continental crust was relatively limited, consisting mainly of small volcanic islands and protocontinents. But during the late Archean and early Proterozoic, the volume of continental crust increased substantially as volcanic activity and tectonic processes built thicker, more stable landmasses. These growing continents weathered more extensively, consuming atmospheric carbon dioxide through the reaction of rainwater with silicate rocks. The burial of organic carbon, dead cyanobacteria, and other organisms in marine sediments also removed carbon from the active carbon cycle, further reducing greenhouse gases. This increase in continental weathering and organic carbon burial may have worked in concert with cyanobacterial oxygen production to trigger the Great Oxygenation Event. Some models suggest that oxygen levels remained low for hundreds of millions of years after cyanobacteria evolved because the continuous influx of volcanic and metamorphic gases consumed the oxygen as fast as it was produced. Only when continental weathering accelerated and reduced the flux of these oxygen-consuming gases did atmospheric oxygen begin to accumulate. This hypothesis links biological innovation with geological processes, showing how life and the physical Earth evolved together as an integrated system. The oxidation of Earth's surface also affected nutrient cycles crucial for life. Phosphorus, an essential element for DNA, RNA, and cell membranes, became more bioavailable in an oxygenated world. In anoxic conditions, phosphorus tends to stay bound in minerals and sediments, but oxidative weathering releases phosphorus into solution where organisms can use it. However, this increased phosphorus availability may have been partially offset by iron oxidation. Ferric iron compounds readily bind phosphorus, removing it from circulation. The complex interplay of these nutrient cycles influence the productivity of marine ecosystems and the pace of evolutionary change. Another consequence of oxygenation was the formation of Earth's ozone layer. Ozone, a molecule consisting of 3 oxygen atoms bonded together, forms when ultraviolet radiation from the sun strikes oxygen molecules in the upper atmosphere. The accumulation of atmospheric oxygen during the Great Oxygenation Event led to ozone formation in the stratosphere, creating a shield against harmful UV radiation. Before the ozone layer existed, UV radiation penetrated Earth's surface with an intensity that would destroy most complex organic molecules and damage DNA. The ozone layer's formation made shallow waters and land surfaces much more hospitable to life, though it will be hundreds of millions of years before organisms fully exploited these newly protected environments. The Great Oxygenation Event also left its mark on the evolution of biochemistry. Organisms evolved sophisticated enzymes to manage oxygen's destructive potential. Catalase and superoxide dismutase, enzymes that break down reactive oxygen species, became essential for survival in oxygenated environments. The evolution of aerobic respiration, using oxygen as the final electron acceptor in metabolism, represented an enormous biochemical innovation that would power all complex life. The electron transport chains that modern eukaryotes use for respiration are variations on systems that first evolved in bacteria during the Proterozoic. By about 1.8 billion years ago, oxygen levels had stabilized. At perhaps 1 to 10% of the atmosphere, and the ocean's surface waters had become oxygenated, though the deep ocean likely remained anoxic for hundreds of millions of years longer. The world had been transformed. Red beds, oxidized sedimentary rocks rich in ferric iron, became common in the geological record, replacing the gray and green rocks characteristic of the anoxic Archean. The stage was set for the next major transition in Earth's history, the evolution of complex cells with nuclei and specialized internal compartments, the eukaryotes that would eventually give rise to all animals, plants, and fungi. The Great Oxygenation Event stands as one of the most profound changes in Earth's history, comparable in significance to the origin of life itself. It was driven by biology, by the metabolic waste product of cyanobacteria, but it transformed geology, chemistry, and climate. It caused mass extinction among anaerobic organisms while opening new opportunities for aerobic life. It demonstrates how life doesn't simply adapt to its environment, but actively reshapes that environment in ways that feed back on evolution. Earth after oxygenation was a fundamentally different planet than Earth before, and the revolution begun by cyanobacteria 2.4 billion years ago continues to shape our world today, as we breathe the oxygen-rich air they made possible. Continental configuration played a crucial role in triggering snowball Earth conditions. During the Cryogenian, the supercontinent Rodinia was breaking apart. Most of Rodinia's landmass was concentrated in tropical latitudes, where weathering rates are highest due to warm, wet conditions. Silicate weathering, the chemical breakdown of rocks by rainwater, consumes atmospheric carbon dioxide, as the rainwater dissolves to form carbonic acid, which then reacts with minerals and rocks. The products of this weathering eventually wash into the ocean and are deposited as carbonate sediments, locking the carbon away. With so much land in the tropics weathering intensely, the rate of carbon dioxide removal from the atmosphere may have exceeded the rate at which volcanoes released it, causing a gradual drawdown of greenhouse gases and cooling the planet toward the glaciation threshold. The breakup of Rodinia itself may have accelerated this process. Continental rifting creates extensive shallow seas and coastlines, increasing the surface area of rock exposed to weathering. Volcanic activity associated with rifting releases fresh, easily weathered rock. Additionally, some scientists propose that the evolution of eukaryotic algae during this period may have increased the biological productivity of the oceans, leading to greater burial of organic carbon in marine sediments, another mechanism for removing carbon from the active carbon cycle and weakening the greenhouse effect. Life during and between the Cryogenian glaciations consisted primarily of single-celled organisms, but an enormously important transition was underway. Eukaryotic cells, cells with a nucleus and other membrane-bound organelles, had evolved earlier in the Proterozoic, with the earliest definitive fossils dating to about 1.6 billion years ago, though molecular evidence suggests they may have originated even earlier, perhaps 2 billion years ago or more. Eukaryotes represented a quantum leap in cellular complexity compared to the simpler prokaryotic bacteria and archaea that had dominated Earth for the preceding 2 billion years. The origin of eukaryotes involved one of the most remarkable events in evolutionary history, endosymbiosis. According to the endosymbiotic theory, first championed by biologist Lynn Margulis in the 1960s, eukaryotic cells arose when one prokaryotic cell engulfed another but didn't digest it. Instead, the engulfed cell survived inside its host, and the two organisms formed a mutually beneficial partnership. Over millions of years, the engulfed cell evolved into an organelle, a specialized compartment within the host cell. Mitochondria, the power plants of eukaryotic cells that perform aerobic respiration, originated from ancient bacteria. In plant cells and algae, chloroplasts, the organelles that perform photosynthesis, originated from cyanobacteria. The evidence for endosymbiosis is overwhelming. Mitochondria and chloroplasts have their own DNA, separate from the nucleus, and this DNA is circular like bacterial DNA rather than linear like eukaryotic nuclear DNA. The DNA sequences show that mitochondria are closely related to a group of bacteria called alpha proteobacteria, while chloroplasts are clearly derived from cyanobacteria. Both organelles reproduce by dividing, just like bacteria, and they have double membranes, the inner membrane from the original bacterial cell and the outer membrane from the engulfing process. This symbiosis allowed eukaryotic cells to harness the efficient energy production of aerobic respiration and, in photosynthetic eukaryotes, to perform oxygenic photosynthesis. The evolution of eukaryotes opened up vast new evolutionary possibilities. Eukaryotic cells could become much larger than prokaryotic cells because their mitochondria provided more energy. They could develop complex internal structures and specialized functions. Crucially, eukaryotes evolved sexual reproduction, the combination of genetic material from two parents, which dramatically accelerated the pace of evolution by shuffling genes and creating new combinations with each generation. Prokaryotes exchange genes through mechanisms like horizontal gene transfer, but sexual reproduction proved far more effective at generating diversity. For hundreds of millions of years after their origin, eukaryotes remained single-celled, though they diversified into many forms. Some were photosynthetic algae, some were predators that engulfed other cells, some formed colonies. The fossil record from this period is frustratingly sparse because these organisms, lacking hard parts like shells or skeletons, are rarely preserved as fossils. What evidence we have comes from microfossils, cells preserved in chert or other fine-grained rocks, and from complex organic molecules called biomarkers that only eukaryotes produce. Steranes, the fossilized remains of sterols found in eukaryotic cell membranes, appear in rocks as old as 1.6 billion years, confirming the presence of eukaryotes. During the late Proterozoic, after the last snowball Earth glaciation ended around 635 million years ago, oxygen levels in the atmosphere and ocean rose substantially, a second oxygenation event sometimes called the Neoproterozoic oxygenation event. Oxygen concentrations climbed from the 1 to 10% range where they had been stuck for over a billion years to perhaps 15% or more of the atmosphere, approaching modern levels. The deep ocean, which had remained largely anoxic since the Archean despite surface oxygenation, finally became oxygenated throughout. This oxygenation may have been triggered by the breakup of Rodinia, which created extensive shallow continental shelves where photosynthetic organisms could thrive, boosting oxygen production. This rise in oxygen concentration was critical for the evolution of complex multicellular life. Large organisms require efficient oxygen delivery to their tissues, which is difficult when oxygen concentrations are low. Single-celled organisms can absorb oxygen across their entire surface, but as organisms become larger, their volume increases faster than their surface area, creating a challenge for getting oxygen to interior cells. Only when atmospheric oxygen rose to sufficient levels could organisms evolve the tissues, circulatory systems, and respiratory structures needed to support large bodies. The stage was now set for the appearance of Earth's first complex multicellular organisms. Around 575 to 541 million years ago, during the Ediacaran period, the final period of the Proterozoic Eon, strange soft-bodied creatures appeared in the oceans. These Ediacaran organisms, named after the Ediacara Hills in South Australia, where they were first discovered in the 1940s, represent some of the most enigmatic fossils in the entire geological record. They were unlike anything alive today, and scientists continue to debate what they were and how they relate to modern animal groups. Ediacaran fossils are typically preserved as impressions in sandstone, where organisms were buried by sudden sediment deposits and left behind molds and casts. The fossils show creatures ranging from a few centimeters to over a meter in length, with diverse forms. Some, like Dickinsonia, were oval-shaped and quilted, resembling flattened air mattresses with repeated segments. Others, like Charnia, were frond-like organisms anchored to the seafloor, resembling plants though they probably weren't photosynthetic. Kimberella had a slug-like form with possible feeding structures. Tribrachidium was disc-shaped with threefold radial symmetry, unlike the bilateral symmetry of most modern animals. Many Ediacaran organisms had a peculiar quilted or fractal construction, with their bodies divided into repeated compartments that may have maximized surface area for absorbing nutrients and oxygen directly from seawater. Some scientists, notably German paleontologist Adolf Seilacher, argued that these organisms represented a failed evolutionary experiment, a kingdom of life fundamentally different from modern animals, plants, or fungi, which went extinct without leaving descendants. Others contend that at least some Ediacaran fossils represent early animals, possibly ancestors or relatives of modern groups like cnidarians, jellyfish and corals, or bilaterians, animals with bilateral symmetry, including most modern animals. Recent discoveries have provided evidence that at least some Ediacaran organisms were indeed early animals. Kimberella shows evidence of a muscular foot and possible grazing traces on microbial mats, suggesting it was a mobile animal. Dickinsonia has been shown through chemical analysis to contain cholesterol and other lipids characteristic of animals. Small shell fossils and trace fossils, burrows and tracks left by organisms moving through sediment, became more common in the late Ediacaran, indicating that active, mobile animals were evolving. The Ediacaran world was vastly different from the oceans we know today. There were no predators with teeth or claws, no shells or skeletons, and probably no eyes. The seafloor was covered with extensive microbial mats, thick layers of bacteria and algae that trapped sediment and formed a kind of living carpet. Many Ediacaran organisms appear to have lived on or in these mats, either absorbing nutrients directly or possibly farming bacteria. The absence of bioturbation, sediment disturbance by burrowing organisms, in early Ediacaran rocks suggests that animals hadn't yet evolved to burrow deeply, though this changed by the late Ediacaran as mobile organisms began reworking. The sediment. Why did complex multicellular life evolve when it did, after 3 billion years of single-cell dominance? The rise in oxygen concentration was certainly a prerequisite, providing the energy budget needed for larger bodies and active lifestyles. The end of snowball Earth glaciations may have created environmental instability that accelerated evolution. Genetic innovations, such as the evolution of Hox genes, master regulatory genes that control body plan development, gave organisms the toolkit to build complex, differentiated bodies. The evolution of predation may have driven an evolutionary arms race, with prey evolving defenses and predators evolving better hunting strategies, though clear evidence for predation doesn't appear until the end of the Ediacaran. Some scientists point to the breakup of Rodinia and subsequent continental collisions as factors that increased habitat diversity, created shallow continental shelves where complex life could flourish, and drove nutrient cycling that supported higher productivity. The late Proterozoic saw continued evolution of the eukaryotic supergroups that would give rise to modern animals, plants, fungi, and various protists. Animals, multicellular heterotrophs with specialized tissues, probably evolved from single-celled ancestors related to choanoflagellates, a group of unicellular eukaryotes that form colonies and share features with the simplest modern animals, the sponges. By the end of the Ediacaran period, around 541 million years ago, some organisms were developing small mineralized structures, the first hard parts in the fossil record. These included tiny conical shells, tubes, and plates made of calcium carbonate or calcium phosphate. The appearance of these structures marked a transition from the soft-bodied Ediacaran fauna to the harder-bodied animals of the upcoming Cambrian period. Many of the classic Ediacaran organisms disappeared from the fossil record around this time, whether due to environmental changes, competition for more advanced animals, or the evolution of predators that could consume them. The Ediacaran-Cambrian boundary represents one of the most significant transitions in Earth's history. The Proterozoic Eon, spanning 2 billion years of gradual change, from the oxygenation of the atmosphere to the evolution of complex cells and finally to the appearance of the first multicellular organisms, was drawing to a close. Earth had transformed from a planet of simple bacteria into one where complex life was poised to explode into an almost incomprehensible diversity of forms. The Phanerozoic Eon, the eon of visible life, was about to begin, and with it would come the most dramatic evolutionary radiation in Earth's history, the Cambrian explosion. Imagine examining Earth from space 550 million years ago, then looking again just 25 million years later. On geological timescales, 25 million years is a heartbeat, yet the transformation in Earth's oceans during this interval was extraordinary. At the beginning of this period, marine life consisted primarily of soft-bodied organisms creeping along microbial mats or swaying with ocean currents. By the end, the seas teemed with an almost modern-looking diversity of body plans, animals with eyes, jaws, claws, shells, and jointed limbs. This rapid diversification, which occurred during the Cambrian period from about 541 to 485 million years ago, is known as the Cambrian explosion, though explosion is perhaps misleading, as the process still took millions of years, just remarkably few by evolutionary standards. The Cambrian explosion represents the sudden appearance in the fossil record of most major animal groups, or phyla, that exist today. Before the Cambrian, fossils are rare and enigmatic. After the Cambrian began, fossils become abundant and clearly recognizable as animals with familiar body plans. Arthropods, the group that includes modern insects, spiders, and crustaceans, appear with segmented bodies, jointed appendages, and hard exoskeletons. Mollusks show up with shells. Chordates, the phylum that includes all vertebrates, make their first appearance. Echinoderms, brachiopods, sponges, cnidarians, and numerous other groups all appear within a relatively narrow window of geological time. The most famous window into Cambrian life comes from exceptional fossil deposits called Lagerstätten, German for storage places, where unusual preservation conditions captured not just hard shells but soft tissues as well. The most celebrated of these is the Burgess Shale in British Columbia, Canada, discovered in 1909 by paleontologist Charles Doolittle Walcott. The Burgess Shale, dated to about 508 million years ago during the Middle Cambrian, contains exquisitely preserved fossils showing details of internal anatomy, digestive systems, eyes, and even the contents of animals' guts. The fossils reveal a marine ecosystem of stunning complexity and diversity, with creatures that seem almost alien in their bizarre adaptations. Walking through a Cambrian ocean would have been simultaneously familiar and strange. The water would have been clear in some areas, murky with sediment in others. Schools of small swimming animals would dart past. Nothing like fish, which hadn't evolved yet, but arthropods and other creatures propelling themselves through the water. The seafloor would be crowded with life in some areas, sponges filtering water, worm-like creatures burrowing through sediment, hard-shelled animals anchored to rocks, and predators prowling for prey. The most striking difference from earlier oceans would be the abundance of hard parts. Shells, plates, spines, and exoskeletons were everywhere, representing a revolution in how organisms protected themselves and interacted with their environment. Trilobites dominated many Cambrian marine environments, and would continue to thrive for the next 270 million years until their final extinction at the end of the Permian period. These arthropods had segmented bodies divided into 3 lobes, hence their name, with numerous legs underneath and a hard exoskeleton of calcium carbonate and calcium phosphate on top. They ranged from less than a centimeter to over 70 centimeters in length. Most crawled along the seafloor, scavenging or hunting small prey, though some were swimmers and others filter feeders. Trilobites had compound eyes, sophisticated visual organs made of numerous separate optical units, making them among the first organisms to develop complex vision. Their eyes used calcite crystals as lenses, an elegant solution to focusing light underwater. The evolution of eyes may have been one of the key drivers of the Cambrian explosion. Being able to see introduced a new dimension to evolution, the ability to find prey from a distance, to avoid predators, to find mates, and to navigate complex environments. Once some animals evolved eyes, selection pressure would have favored their prey developing better defensive adaptations and their predators developing better hunting strategies. This evolutionary arms race could have rapidly driven the diversification of body forms, behaviors, and ecological strategies that characterized the Cambrian explosion. Among the most fearsome predators of the Cambrian seas was Anomalocaris, whose name means abnormal shrimp. Though it was neither abnormal nor a shrimp by modern standards, it was simply unlike anything paleontologists had seen when fragments were first discovered in the late 1800s. For decades, scientists misidentified parts of this creature. Its circular mouth was thought to be a jellyfish, its grasping appendages were classified as shrimp bodies, and its body segments were considered sea cucumbers. Only when complete fossils were found in the Burgess Shale did researchers realize these pieces belonged to a single enormous predator up to a meter in length, a giant by Cambrian standards when most animals measured only centimeters. Anomalocaris had a segmented body with lateral lobes used for swimming, large compound eyes on stalks, and 2 spiny appendages at the front that could grasp and manipulate prey. Its circular mouth, lined with plates arranged like a pineapple ring, could constrict to crush hard-shelled prey. Bite marks matching Anomalocaris' mouth structure have been found on trilobite fossils, providing direct evidence of predation. This creature represented a new ecological role, the apex predator, and its presence would have shaped the evolution of defensive adaptations in other animals. The Burgess Shale fauna includes dozens of bizarre organisms that challenge our understanding of animal evolution. Opabinia had 5 eyes and a long, flexible proboscis with grasping claws at the end, used to capture small prey and bring them to its mouth located underneath its head. Hallucigenia was covered in spines and walked on paired legs, though paleontologists initially reconstructed it upside down and backwards due to its strange anatomy. Wiwaxia was covered in protective scales and spines, possibly related to mollusks or annelid worms. These creatures demonstrate that early animal evolution was experimenting with body plans and combinations of features that have no modern equivalents. China's Qinjiang fossil site, slightly older than the Burgess Shale at about 518 million years, provides another spectacular window into Cambrian life. Discovered in 1984 in Yunnan province, the Xinjiang fauna includes over 250 species with exceptional preservation of soft tissues. Among the most significant discoveries are early chordates, members of our own phylum. Miloconmingia and Haequichthyes were small, fish-like creatures with notochords, the flexible rod that precedes the evolution of a backbone, gill slits, and segmented muscles. These represent some of the earliest known vertebrate ancestors, showing that our lineage was present from the early Cambrian, though vertebrates wouldn't dominate marine ecosystems for another 100 million years. Why did the Cambrian explosion happen when it did? Scientists have proposed numerous explanations, and the answer likely involves multiple factors working together. The rise in atmospheric oxygen to near-modern levels provided the energy budget needed for active lifestyles, complex tissues, and the metabolic cost of building shells and exoskeletons. The evolution of predation created an evolutionary arms race where prey evolved defensive structures like shells and spines, while predators evolved mechanisms to overcome these defenses. This feedback loop would have accelerated morphological diversification. Genetic innovations played a crucial role. The Hox genes master. Regulatory genes that control where different body parts develop had evolved by the Cambrian and allowed organisms to build complex, differentiated body plans with repeated segments and specialized appendages. Small changes to these regulatory genes could produce large changes in body form, enabling rapid evolutionary experimentation. The evolution of developmental flexibility meant that mutations could generate novel body plans that natural selection could then test. Environmental factors also contributed. The breakup of the supercontinent Rodinia had created extensive shallow continental shelves, productive marine environments with high nutrient levels and abundant habitats. Ocean chemistry was changing, with calcium concentrations increasing to levels that made biomineralization, the construction of shells and skeletons, energetically feasible. The disappearance of widespread microbial mats from the seafloor, disrupted by burrowing animals, changed substrate conditions and created new ecological opportunities. Some scientists invoke ecological theory, arguing that early Cambrian ecosystems had numerous empty niches, ecological roles that no organism had yet evolved to fill. The first animals to evolve adaptations for particular lifestyles faced little competition and could diversify rapidly. This is similar to adaptive radiations observed on isolated islands, where a single colonizing species diversifies to fill many ecological roles. As niches filled and competition increased, the pace of body plan innovation slowed, leaving us with a major phyla established during the Cambrian. The Cambrian oceans also saw the evolution of biomineralization on a massive scale. Before the Cambrian, only rare organisms produced hard parts. During the Cambrian, numerous groups independently evolved the ability to precipitate minerals, primarily calcium carbonate or calcium phosphate, into protective shells, supportive skeletons, or defensive spines. This mineralization revolution transformed marine ecosystems and the fossil record itself, as hard parts preserve far more readily than soft tissues. The abundance of Cambrian fossils compared to earlier periods partly reflects this preservation bias, though the genuine increase in diversity and abundance is undeniable. Different animal groups solve the mineralization challenge in different ways, using various minerals and construction techniques. Mollusks secreted calcium carbonate shells in layered structures that combined strength with relative lightness. Brachiopods, which superficially resemble clams but are unrelated, build shells from calcium carbonate or calcium phosphate with different internal structures. Arthropods constructed exoskeletons from chitin reinforced with calcium carbonate, creating armor that was both protective and flexible at the joints. Echinoderms developed an internal skeleton of calcite plates that could grow with the animal, unlike the molted exoskeletons of arthropods. The evolution of hard parts had cascading effects on marine ecosystems and biogeochemical cycles. Shell-building organisms began extracting vast quantities of calcium from seawater, altering ocean chemistry, and creating massive deposits of limestone that would eventually form mountain ranges like the Rockies and Himalayas. When these organisms died, their shells accumulated on the seafloor, creating carbonate sediments that buried organic carbon and helped regulate atmospheric carbon dioxide levels. The carbon cycle became increasingly influenced by biological processes rather than purely geological ones. Cambrian reefs differed dramatically from modern coral reefs. True corals hadn't evolved yet, so Cambrian reefs were built primarily by archaeocyaths, extinct sponge-like organisms with porous, cup-shaped calcium carbonate skeletons. These creatures flourished in the early to middle Cambrian, building substantial reef structures in shallow tropical seas. They filtered seawater for food particles and provided habitat for numerous other organisms. However, archaeocyaths went extinct by the end of the Middle Cambrian, possibly due to environmental changes or competition with other filter feeders, and millions of years would pass before other organisms evolved to fill the reef-building niche. The Cambrian seafloor was transformed by bioturbation, the reworking of sediment by burrowing organisms. Before the Cambrian, sediments typically formed neat horizontal layers, with microbial mats binding the surface. During the Cambrian, worms and other organisms began burrowing extensively, mixing sediment layers and disrupting microbial mats. This bioturbation oxygenated deeper sediment layers, released nutrients, and created new ecological niches. The depth and intensity of bioturbation increased throughout the Cambrian, fundamentally altering sediment structure in ways that persisted throughout the rest of Earth's history. Not all Cambrian animals lived on or in the seafloor. The water column supported diverse swimming organisms, from tiny arthropods to larger predators. Some trilobites were adapted for swimming rather than crawling. Various worm-like creatures undulated through the water. The evolution of active swimming required sophisticated neuromuscular coordination and sensory systems to navigate three-dimensional space, driving the evolution of more complex nervous systems and brains. The oldest known fossilized brains come from Cambrian arthropods preserved in exceptional detail, showing that sophisticated neural processing had evolved remarkably early. By the Middle Cambrian, around 510 million years ago, marine ecosystems had developed recognizable ecological structures with multiple trophic levels. Primary producers, cyanobacteria and algae, captured energy from sunlight through photosynthesis. Herbivores and filter feeders consumed these primary producers or fed on organic particles suspended in water. Small predators hunted the herbivores, while apex predators like Anomalocris hunted smaller predators and large prey. Scavengers cleaned up dead organisms and waste products. Decomposers, primarily bacteria, recycled nutrients from dead organic matter. This complex food web structure, with energy flowing from producers through multiple consumer levels, established the basic ecological template that persists today. The geographic distribution of Cambrian life was influenced by continental positions and ocean currents. During the early Cambrian, most continental landmasses were located in the southern hemisphere or near the equator. The supercontinent Gondwana was assembling from separate continental fragments including present-day South America, Africa, Antarctica, Australia, and India. Other continents like Laurentia, ancestral North America, Baltica, northern Europe, and Siberia existed as separate landmasses. Shallow seas flooded the continental margins, creating extensive shelf environments where Cambrian life flourished. Deep ocean basins between continents would have supported different communities, though we have less fossil evidence from deep water environments. Climate during the Cambrian was generally warm with no evidence for polar ice caps. Carbon dioxide levels were substantially higher than today, creating a greenhouse climate with reduced temperature differences between equator and poles. Sea levels were high, flooding low-lying continental areas and creating vast shallow water environments. Ocean circulation patterns driven by temperature and salinity differences distributed heat and nutrients globally, though the details of these patterns remain uncertain due to limited evidence. The Cambrian period witnessed one of the most profound transformations in Earth's history, the establishment of complex animal ecosystems that would set the template for the next 500 million years of evolution. When the Cambrian ended around 485 million years ago, the oceans were unrecognizably different from their Precambrian state. The stage was now set for life's next great challenge, the colonization of land. For the first 4 billion years of Earth's history, land was a barren wasteland. Volcanic rocks, wind-swept deserts, and lifeless river valleys stretched across the continents with no sound except the wind and the crash of waves against the shore. Life remained confined to the water, oceans, lakes, rivers, and perhaps damp soils at the water's edge. The land offered tremendous opportunities, abundant sunlight for photosynthesis, escape from marine predators, and vast uninhabited territory. But it also presented formidable challenges. Organisms had to prevent desiccation in the air, support their bodies without the buoyancy of water, reproduce without aquatic larvae, and obtain nutrients from rock and soil rather than from dissolved minerals in the ocean. The conquest of land required profound evolutionary innovations and would transform Earth's surface as dramatically as the Cambrian explosion transformed the oceans. The transition began during the Ordovician period from about 485 to 444 million years ago, when the first pioneers ventured onto land. These weren't animals but photosynthetic organisms, initially cyanobacteria and algae that formed thin crusts on rocks near water, then simple plants that evolved from green algae. The earliest plant fossils come from the Middle Ordovician, around 470 million years ago, preserved as spores with thick, decay-resistant walls that protected the reproductive cells from drying out. These spores resemble those of modern bryophytes, mosses, liverworts, and hornworts, suggesting the first land plants were small, low-growing organisms without true roots, stems, or leaves. These pioneering plants faced the desiccation problem head-on by evolving a waxy cuticle, a waterproof coating that covered their surfaces and prevented water loss. However, a complete waterproof coating would also prevent gas exchange needed for photosynthesis. The solution was stomata, microscopic pores that could open to allow carbon dioxide in and oxygen out, then close to conserve water. This innovation, still used by all land plants today, allowed organisms to balance the competing demands of gas exchange and water retention. The earliest land plants also developed specialized tissues for transporting water and nutrients, the evolutionary precursors to the sophisticated vascular systems of later plants. The colonization of land by plants had profound effects on the terrestrial environment. Plant roots and associated fungi began breaking down rock through both mechanical fracturing and chemical weathering, accelerating the formation of soil, a complex mixture of minerals, organic matter, water, and air that would become essential for terrestrial ecosystems. As plants died and decomposed, their organic matter enriched the soil, creating habitats for bacteria, fungi, and eventually small animals. The presence of plants reduced erosion by stabilizing soil with root networks, altered water cycles by intercepting rainfall and releasing water through transpiration, and began drawing down atmospheric carbon dioxide through photosynthesis and burial of organic carbon. By the Silurian period, from 444 to 419 million years ago, land plants had diversified and grown more substantial. Cooksonia, one of the best-known early land plants from the late Silurian around 425 million years ago, stood only a few centimeters tall but represented a significant advance. It had branching stems with spore-producing structures at the tips and a simple vascular system for transporting water. Cooksonia and its relatives formed low carpets of vegetation in moist areas near water, resembling miniature versions of later forests. These early plant communities provided the first terrestrial food sources and habitats, setting the stage for animal colonization. Arthropods were the first animals to successfully colonize land, which makes sense given their pre-existing adaptations. Their exoskeletons provided structural support without water's buoyancy and protection against desiccation. Their jointed legs were well suited for walking on solid surfaces. Many marine arthropods already had sophisticated sensory systems and nervous systems capable of coordinating complex behaviors. The transition still required significant adaptations, particularly developing ways to breathe air rather than extracting oxygen from water, and modifying reproduction to work in terrestrial environments. The earliest evidence of land animals comes from trackways, fossilized footprints, found in Ordovician rocks from around 450 million years ago. These tracks were made by arthropods, possibly millipede-like creatures or early relatives of insects, that crawled across mudflats or sandy shores. By the Silurian, definitive body fossils of terrestrial arthropods appear, including primitive centipedes, millipedes, and possibly early arachnids. These animals were small, probably living in the moist soil among early plants, feeding on decaying plant matter, fungi, bacteria, or each other. They breathed through simple tracheal systems, networks of tubes that delivered air directly to tissues, an efficient system for small organisms that remains the primary breathing mechanism for insects today. The Devonian period, lasting from 419 to 359 million years ago, witnessed the full establishment of terrestrial ecosystems and is sometimes called the Age of Fishes for reasons we'll explore in the next chapter. On land, plants underwent remarkable radiation in size and complexity. Vascular plants, those with specialized tissues for transporting water and nutrients, evolved lignin, a complex organic polymer that stiffened cell walls and allowed plants to grow tall and woody. This innovation enabled the evolution of trees, transforming the landscape from low carpets of vegetation into the first forests. By the Middle Devonian, around 385 million years ago, forests of primitive trees spread across the continents. These weren't forests as we know them today. The trees belonged to groups that are now extinct or reduced to small representatives. Archaeopteris, one of the first tree-sized plants, grew up to 30 meters tall with a woody trunk and branches bearing fern-like fronds. Despite its tree-like appearance, Archaeopteris reproduced through spores rather than seeds and is classified as a progymnosperms, an evolutionary intermediate between ferns and seed plants. These ancient forests covered floodplains and river valleys, their roots digging deep into the soil, and their canopies creating shaded understories where smaller plants, fungi, and arthropods thrived. The evolution of roots had revolutionary consequences for Earth's surface. Deep root systems penetrated several meters into bedrock, fracturing stone and accelerating chemical weathering far beyond what algal and bacterial crusts could achieve. This enhanced weathering consumed atmospheric carbon dioxide at unprecedented rates as silicate rocks reacted with acidic soil water rich in carbon dioxide from plant respiration and decomposition. Some models suggest that Devonian plant colonization drew down so much carbon dioxide that atmospheric concentrations dropped by as much as 90%, weakening the greenhouse effect and contributing to global cooling that eventually triggered glaciation in the late Devonian. Plants also evolved increasingly sophisticated reproductive strategies. Early land plants released spores that developed into separate gametophyte generations, small organisms that produce sperm and eggs. This system required water for the swimming sperm to reach eggs, limiting these plants to moist environments. During the Devonian, some plants evolved heterospory, the production of two different types of spores, small male spores and larger female spores, which eventually led to the evolution of seeds in the late Devonian around 365 million years ago. Seeds package the embryonic plant with a food supply and protective coating, allowing reproduction without standing water and enabling plants to colonize drier environments. Terrestrial animal diversity exploded during the Devonian. Arthropods evolved into numerous forms filling different ecological niches. Herbivorous millipedes fed on plant material and detritus. Predatory centipedes hunted smaller arthropods. The first insects appeared, initially wingless and small, living in soil and leaf litter. Arachnids diversified into early spiders, scorpions, mites, and other groups. Some Devonian scorpions were enormous by modern standards, with species reaching 70 centimeters in length, though whether these giants lived in water, on land, or both remains debated based on their gill-like respiratory structures. The most significant animal invasion of land during the Devonian involved vertebrates, our own group. The first tetrapods, four-legged vertebrates, evolved from lobe-finned fish that lived in shallow freshwater environments prone to seasonal drying. These fish had muscular, bone-supported fins that could be used to prop up the body or even crawl across mudflats between pools. They also had primitive lungs for supplementing gill respiration when water became oxygen poor. Natural selection favored individuals better at surviving on land, gradually transforming these fish into amphibians. Tiktaalik, discovered in 2004 in Devonian rocks from Arctic Canada, dated to about 375 million years ago, represents a spectacular transitional form. This creature had a fish-like body with scales and fins, but its front fins contained bones corresponding to the humerus, radius, and ulna of tetrapod. Forelimbs. It had a flattened head with eyes on top like a crocodile, a mobile neck unusual for fish, and ribs strong enough to support the body when propped up on its fins. Tiktaalik could breathe air through primitive lungs and probably spent considerable time in shallow water or even on land, using its strong fins to crawl between pools or hunt in very shallow water. Shortly after Tiktaalik in the fossil record, we find definitive tetrapods with digits rather than fin rays. Acanthostega and Ichthyostega from about 365 million years ago in what is now Greenland had four limbs with 8 and 7 digits respectively. The standard five-fingered pattern evolved later. These animals were still primarily aquatic, with internal gills for underwater breathing alongside lungs for air breathing, and limbs better suited for swimming or pulling through aquatic vegetation than for walking on land. But they represent crucial steps in the transition from water to land, showing that limbs evolved initially for aquatic locomotion and were only later adapted for terrestrial walking. The late Devonians saw continued evolution of tetrapods, though a mass extinction event around 375 to 359 million years ago. The late Devonian extinction temporarily slowed diversification. This extinction, actually a series of pulses rather than a single event, eliminated many marine species, particularly in tropical reefs, possibly due to ocean anoxia, climate cooling, asteroid impacts, or a combination of factors. On land, the extinction's effects were less severe, and terrestrial ecosystems continued developing through the subsequent Carboniferous period. By the end of the Devonian, land ecosystems had developed recognizable ecological structures. Plants formed the primary producers, capturing solar energy through photosynthesis. Herbivorous arthropods fed on living plants, while the tridivores consumed dead plant material. Predatory arthropods and early tetrapods hunted the herbivores and detritivores. Fungi and bacteria decomposed dead organisms, recycling nutrients back into the soil. These food webs were less complex than modern terrestrial ecosystems, with fewer species and simpler interactions, but they established the basic template that would persist and elaborate in subsequent periods. The evolution of jawed fish during the Silurian and Devonian was equally revolutionary, though it played out primarily in aquatic environments. Early fish, like their ancestors from the Cambrian, lacked jaws and fed by filtering water or sucking up sediment. The evolution of jaws from modified gill arches, bony supports for the gills, opened up new feeding strategies and drove explosive diversification of fish groups. Jawed fish could bite off chunks of food, attack and consume larger prey, and process tough food items like shellfish and tough plant material. This innovation would eventually lead to fish dominating aquatic ecosystems and ultimately give rise to all terrestrial vertebrates, since tetrapods inherited their jaws from fish ancestors. The Devonian fish fauna included numerous groups, many now extinct. Placoderms, or plated skins, were armored fish with bony plates covering their heads and front bodies and jaws equipped with sharp bony plates rather than teeth. Dunkleistus, one of the largest placoderms at up to 10 meters long, was an apex predator with blade-like jaws capable of generating tremendous bite forces. These fish ruled Devonian seas until their extinction at the end of the period. Other jawed fish groups that appeared in the Devonian include the ancestors of modern sharks and rays, bony fish that would eventually dominate aquatic environments, and the lobe-finned fish that gave rise to tetrapods. The Devonian also saw the evolution of sharks and their relatives. Fish with skeletons made of cartilage rather than bone. Early sharks were smaller and less specialized than many modern species, but they already possessed the streamlined bodies, multiple rows of replaceable teeth, and keen senses that would make their descendants successful predators for the next 400 million years. Some Devonian sharks had peculiar features lost in later species, such as Stethecanthus with its anvil-shaped spine covered in tooth-like denticles, possibly a display structure for mating or intimidation. On land, the late Devonian landscape would have looked increasingly familiar, at least from a distance. Forests covered river valleys and floodplains, with trees reaching 30 meters or more in height. Fallen logs decomposed slowly on the forest floor, home to countless arthropods, fungi, and microorganisms. Rivers and streams teemed with fish and early tetrapods. But up close, the strangeness would be apparent. There were no birds, no mammals, no flowering plants, no grass, no large land animals. The dominant sounds would have been wind through the branches, the buzzing and clicking of arthropods, and perhaps the splashing of tetrapods in the water. The forests themselves consisted of unfamiliar tree species bearing spores rather than seeds, with no recognizable flowers or fruits. The conquest of land represented one of evolution's greatest achievements and set the stage for all subsequent terrestrial life. Plants provided the primary productivity to support food webs, generated oxygen through photosynthesis, created soil through their roots, and modified climate through their effects on the carbon cycle and water cycle. Arthropods became the first terrestrial consumers and established the basic ecological roles that would persist through later diversification. Tetrapods made their first tentative steps onto land, beginning the evolutionary journey that would lead to amphibians, reptiles, mammals, and birds. By the end of the Devonian period 359 million years ago, the continents were no longer barren. They were living, breathing, evolving ecosystems that would only grow more complex and diverse in the periods to come. While plants and arthropods were colonizing the land during the Silurian and Devonian periods, an equally momentous transformation was occurring in the oceans, lakes, and rivers. Fish, vertebrates with gills, fins, and streamlined bodies adapted for swimming, underwent an explosive radiation that would establish them as the dominant vertebrates in aquatic environments, a position they maintain today. The Devonian period from 419 to 359 million years ago is sometimes called the Age of Fishes, and for good reason. During this 60 million year span, nearly all major groups of fish appeared, evolved, and diversified, filling ecological roles from tiny filter feeders to enormous apex predators. This radiation fundamentally reshaped aquatic ecosystems and ultimately gave rise to all terrestrial vertebrates, including ourselves. Fish had existed since the Cambrian, but these early vertebrates were jawless, lacking the hinged biting apparatus that would prove so crucial for later success. The most primitive fish, represented today only by lampreys and hagfish, use circular sucking mouths to feed on organic matter, parasitize other fish, or scavenge dead animals. During the Ordovician and Silurian, various groups of armored jawless fish called ostracoderms thrived in marine and freshwater environments. These fish had bony plates covering their heads and front bodies, providing protection from predators, particularly the large predatory arthropods like sea scorpions that dominated Paleozoic waters before jawed fish evolved. The evolution of jaws during the Silurian period around 440 million years ago represents one of the most important innovations in vertebrate history. Jaws evolved from the first or second gill arch, paired bones that supported the gills in jawless ancestors. Through a process paleontologists can trace in the fossil record, and by comparing living fish, these gill arches gradually modified into hinged structures at the front of the skull capable of opening and closing. The upper jaw attached to the skull while the lower jaw articulated with both the skull and upper jaw, creating a lever system that could generate powerful biting forces. Jaws revolutionized vertebrate feeding ecology. Rather than filtering water or sucking up sediment, jawed fish could bite off chunks of food, attack and consume prey much larger than their mouths, crush hard-shell prey, tear flesh, and process tough materials. This opened up an entire spectrum of feeding strategies and enabled fish to compete effectively with arthropods and other invertebrates for dominance of aquatic ecosystems. Within a few million years of jaws evolving, jawed fish had diversified into numerous groups, and many jawless fish lineages went extinct, unable to compete with their more versatile jawed relatives. The first jawed fish belonged to a group called acanthodians, or spiny sharks, though they weren't actually sharks. These small fish, typically 10 to 20 centimeters long, had streamlined bodies covered in small scales, fins supported by spines, and distinctively shaped jaws with multiple tooth whorls. Acanthodians appeared in the late Ordovician or early Silurian and diversified throughout the Devonian in both marine and freshwater environments. They occupied various ecological niches. Some were predators, others filter feeders, some bottom dwellers. Acanthodians survived until the early Permian but eventually went extinct, though they may be related to the ancestors of modern bony fish or sharks. The Devonian witnessed the rise and dominance of placoderms, the armor-jawed fish mentioned briefly in the previous chapter. Placoderms were extraordinarily diverse, with over 400 described species ranging from a few centimeters to 10 meters in length. Their defining characteristic was the bony armor covering their heads and the front portion of their bodies, articulated with the rear portion of the body through a joint that allowed some flexibility. Instead of teeth, most placoderms had sharp bony plates that could shear through flesh and shell. Different placoderm groups adapted to different lifestyles. Some lived in freshwater streams, others in shallow marine environments, still others in the deep ocean. Dunkleistus torelli represents the apex of placoderm evolution. This massive predator reached lengths of 8 to 10 meters and weights approaching a ton, making it one of the largest animals of the Devonian. Its head armor was up to 5 centimeters thick, providing formidable protection, while its blade-like jaw plates created a bite as powerful as that of modern alligators or great white sharks. Biomechanical studies suggest Dunkleistus could open its mouth in less than 1/50th of a second, creating powerful suction that pulled prey into its jaws. Fossilized regurgitated meals containing partially digested fish show that Dunkleistus sometimes bit off more than it could swallow, literally. This fish was the apex predator of Devonian seas, feared by everything that swam. Despite their success, placoderms went extinct at the end of the Devonian during the late Devonian extinction event, along with many other marine groups. The reasons remain debated, possibly climate change, ocean anoxia, competition with other fish groups, or simply bad luck during a time of environmental stress. Their extinction cleared ecological space that will be filled by the two great groups of jawed fish that dominate modern waters, the chondrichthyans, sharks, rays and chimeras, and the osteichthyans, bony fish. Chondrichthyans are characterized by skeletons made of cartilage rather than bone. This might seem like a primitive feature, and indeed early vertebrates had cartilaginous skeletons, but modern sharks represent a derived condition where bone was secondarily lost. Cartilage is lighter than bone and requires less calcium to build, providing advantages in buoyancy and energy economy. Shark scales, called dermal denticles, are actually tiny tooth-like structures that reduce drag and may provide antibacterial properties. Sharks also evolved multiple rows of replacement teeth that move forward like a conveyor belt throughout the animal's life, ensuring they always have functional teeth despite wear and breakage. Early sharks from the Devonian were smaller and less specialized than many living species. They had less streamlined bodies, less sophisticated fins, and in many cases peculiar features that seem bizarre to modern eyes. Stephacanthus, mentioned earlier, had a dorsal fin covered in denticles with a flat, anvil-shaped top. Its function remains mysterious, though display for courtship or species recognition seems likely. Helicoprion, from the later Permian but worth mentioning, had a circular tooth whorl that spiraled like a saw blade. Paleontologists initially thought it was an external structure, but now understand it was located inside the lower jaw, possibly used for cutting soft-bodied prey like squid. By the Carboniferous period following the Devonian, sharks had diversified into many forms. Some resembled modern sharks in having streamlined torpedo shapes, optimized for fast swimming. Others were flattened bottom dwellers, the ancestors of modern rays and skates. Still others had peculiar body forms that don't fit modern categories. Shark diversity peaked during the Carboniferous and Permian, then declined during the Mesozoic before recovering in the Cenozoic. Modern sharks, despite their reputation as living fossils, are actually quite derived and specialized compared to their Paleozoic ancestors. Bony fish, the group that includes virtually all familiar fish like salmon, bass, tuna, goldfish, and countless others, also originated in the Devonian and quickly diversified. Bony fish have skeletons made of calcified bone, operculum, gill covers, that protect the gills and enable more efficient respiration, and swim bladders or lungs that provide buoyancy control. The swim bladder, an air-filled sac that can be inflated or deflated to adjust buoyancy, allowed bony fish to maintain position in the water column without constantly swimming like sharks must. In some primitive bony fish, this structure functioned as a lung for breathing air, and this is the evolutionary precursor of tetrapod lungs. Bony fish split early in their evolution into two major groups, the ray-finned fish, actinopterygians, and the lobe-finned fish, sarcopterygians. Ray-finned fish have fins supported by thin bony rays or spines, while lobe-finned fish have fleshy, muscular fins supported by a single bone articulating with the body. This distinction might seem minor, but it had profound evolutionary consequences. Ray-finned fish would eventually dominate aquatic environments, comprising over 30,000 species today and representing about half of all vertebrate species. Lobe-finned fish would remain relatively uncommon in terms of species numbers, but one lineage would give rise to tetrapods and thus to all terrestrial vertebrates. The Devonian freshwater and marine environments where these fish evolved were vastly different from modern waters. Continents were configured differently, with Gondwana in the south, Laurussia, the merged continents of Laurentia and Baltica, in the equatorial zone, and several smaller continents. Coral reefs, built by tabulate and rugose corals along with stromatoporoids, reef-building sponges, fringe the continental margins in tropical waters. These reefs supported diverse communities of fish, trilobites, brachiopods, crinoids, stalked relatives of starfish, and countless other marine invertebrates. Freshwater environments during the Devonian were becoming increasingly important as fish habitats. Rivers, lakes, and swamps covered portions of the continents, fed by rainfall and runoff from the newly forested landscapes. These freshwater systems experienced fluctuating conditions. Seasonal droughts could cause pools to shrink and oxygen levels to drop, while floods could connect previously isolated water bodies. Such variable conditions favored fish capable of tolerating low oxygen, breathing air, or even moving across land between pools. It was in these challenging freshwater environments that lobe-finned fish evolved the features that would eventually allow their descendants to colonize land. Lobe-finned fish during the Devonian included several groups, most of which are now extinct or reduced to just a few species. Lungfish, capable of breathing air through primitive lungs and surviving in oxygen-poor water or even in mud during droughts, were common and diverse in Devonian freshwaters. Modern lungfish, found in Australia, Africa, and South America, are the surviving remnants of this once diverse group. Coelacanth, another group of lobe-finned fish, were thought extinct since the Cretaceous until a living specimen was caught off South Africa in 1938, causing scientific sensation. Coelacanth have fleshy, muscular fins and other features linking them to the ancestry of tetrapods. The most significant lobe-finned fish for our story are the Elpistostigalians, a group that includes Chictalic, Panderichthes, and other species that represent transitions between fish and tetrapods. These animals show a mosaic of fish and tetrapod features, fish-like tails and scales combined with tetrapod-like skulls, necks, and fins containing bones homologous to tetrapod limb bones. They lived in shallow freshwater environments, possibly in tidal flats or estuaries where water levels fluctuated. The evolution of these transitional forms demonstrates how major evolutionary transitions occur through accumulation of small changes, each advantageous in its particular environment, rather than through sudden jumps. Why did some fish evolve to venture onto land? The traditional explanation emphasized escape from aquatic predators or exploitation of terrestrial food sources, but modern interpretations focus on the challenges of Devonian freshwater environments. Seasonal droughts caused pools to shrink and become oxygen depleted. Fish capable of breathing air could survive these conditions. Those capable of using their fins to prop up their bodies could orient themselves toward the surface for breathing. Eventually, individuals capable of crawling from a drying pool to a nearby one with water would have a survival advantage. The evolution of terrestrial locomotion may have initially been an adaptation for moving between aquatic habitats rather than for living permanently on land. The anatomy of lobe-finned fish pre-adapted them for terrestrial locomotion in several ways. Their fleshy fins contain bones and muscles capable of supporting and moving the body. Their robust ribs could support the body's weight when out of water, preventing the lungs from being compressed. Their ability to breathe air meant they could survive without gill respiration. Their lateral line system, which detects pressure waves in water, could be modified to detect vibrations in air and ground. These features, which evolved for life in shallow, variable freshwater environments, turned out to be highly advantageous for terrestrial life. By the end of the Devonian, true tetrapods with digits and limbs clearly adapted for life on land were beginning to appear, though they would not fully diversify until the subsequent Carboniferous period. Meanwhile, fish continued to dominate aquatic environments. The late Devonian extinction removed placoderms from the picture, but sharks, ray-finned fish, and the remaining lobe-finned fish filled the vacated ecological roles. Bony fish would continue evolving throughout the subsequent periods, eventually developing the incredible diversity we see today. The age of fishes left a lasting legacy. Fish established vertebrates as dominant aquatic predators and consumers, a role they maintained 400 million years later. The evolution of jaws provided vertebrates with feeding versatility that enabled them to compete with arthropods and mollusks. The diversification of fish body plans, fin structures, and sensory systems created templates that would be modified for terrestrial life. Most importantly, one lineage of lobe-finned fish gave rise to tetrapods, carrying vertebrate life onto land and ultimately leading to amphibians, reptiles, mammals, and birds. The oceans, lakes, and rivers at the end of the Devonian were recognizably modern in their basic ecological structure, dominated by fish rather than invertebrates, with complex food webs and diverse species filling specialized niches. The next period, the Carboniferous, would see continued evolution and diversification of fish, but the most dramatic changes would occur on land, where plants and animals would create Earth's first great forests, and the arthropods and tetrapods living among them would evolve to enormous sizes in the oxygen-rich atmosphere. The age of fishes had set the stage. Now it was time for the continents to truly come alive. I'll now continue with the remaining chapters 9 to 13 to complete the full 20,000-word script, maintaining the same documentary style, factual accuracy, and structure with 3 parts per chapter, each part exceeding 500 words. Step into a Carboniferous forest 320 million years ago, and the first thing you notice, aside from the oppressive humidity, would be the sheer strangeness of the trees. They wouldn't look quite like any modern forest. Towering scale trees called lepidodendron, reaching heights of 30 meters, had trunks covered in diamond-shaped leaf scars that gave them a reptilian appearance. Club mosses that today grow only inches tall were represented by forest giants. Cordaites, early relatives of conifers, stretched toward a sky that would seem unusually bright. Atmospheric oxygen had climbed to perhaps 35%, compared to today's 21%, making the air richer and fires more intense. This oxygen-rich world would enable arthropods and other animals to grow to sizes never seen before or since. The Carboniferous period, lasting from 359 to 299 million years ago, takes its name from the vast coal deposits formed during this time, carbon-rich rocks that power the Industrial Revolution and continue to influence our climate today. These coal seams, sometimes dozens of meters thick and extending across hundreds of square kilometers, represent the compressed remains of Carboniferous forests. Dead plant material accumulated in swamps faster than it could decompose, burying vast quantities of carbon that would otherwise have returned to the atmosphere as carbon dioxide. This burial of organic carbon had profound effects on atmospheric composition, climate, and the evolution of life. The Carboniferous is typically divided into two subperiods, the Mississippian, 359 to 323 million years ago, and the Pennsylvanian, 323 to 299 million years ago. The Mississippian saw the recovery of terrestrial and marine ecosystems from the late Devonian extinction and expansion of forests across equatorial regions. The Pennsylvanian witnessed the peak of coal forest development and the evolution of the first reptiles and the largest arthropods ever to live. Climate shifted dramatically during the period, from warm and humid conditions in the early Carboniferous to cooler, more variable conditions by the late Carboniferous, with glaciation affecting the southern supercontinent Gondwana. The forests themselves were unlike anything in the modern world. The dominant trees were like copsids, club mosses, and their relatives, that in today's world are represented only by small ground cover plants. Lepidodendron and its close relative Sigillaria grew rapidly to heights of 30 meters or more, but had surprisingly shallow root systems called stigmaria that spread horizontally, rather than reaching deep into the ground. These trees were supported by thick bark rather than solid wood, making them vulnerable to wind damage. They grew in dense stands in swampy lowlands, their trunks supporting a crown of long, grass-like leaves at the top. When they reproduced, they did so prodigiously, producing huge cone-like structures packed with spores, then often dying after this single reproductive effort. Other trees included the cordoites, primitive conifers that could reach 30 meters tall with strap-like leaves up to a meter long. Seed ferns, despite their name not true ferns but an extinct group of seed plants, grew as trees, shrubs, and climbing vines. True ferns carpeted the forest floor, along with horsetails, some reaching tree size with heights of 15 meters, though most were smaller. The forest understory was dense with vegetation, creating a layered structure that provided numerous microhabitats for animals. The forests thrived particularly in equatorial regions where continents were positioned during the Carboniferous. North America and Europe were located near the equator, merged into a single continent called Euramerica or Laurussia. Tropical conditions, warm temperatures, high rainfall, and minimal seasonal variation prevailed across much of this landmass. Vast lowland areas flooded periodically by shallow seas created perfect conditions for swamp forests. When sea level rose, the swamps were inundated and buried under marine sediments. When sea level fell, the swamps returned. This cyclical flooding and exposure, controlled by the growth and melting of glaciers in Gondwana to the south, created the characteristic layered sequences of coal and marine sediments found in Carboniferous rocks. The accumulation of plant material in these swamps was extraordinary. In modern tropical swamps, bacteria and fungi decompose dead plants relatively quickly, recycling nutrients. But during the Carboniferous, the biochemical machinery for breaking down lignin, the complex polymer that makes wood woody, had not fully evolved. Bacteria and fungi could attack and decompose some plant tissues, but lignin-rich would resist decay. This allowed dead trees to accumulate in swamps, layer upon layer, building up deposits of partially decayed plant material called peat. As more material accumulated on top, the deeper layers were compressed, water was squeezed out, and chemical changes transformed the peat first into lignite brown coal, then bituminous coal, and with enough heat and pressure anthracite. The ecological effects of this carbon burial were profound and global in scope. Photosynthesis removes carbon dioxide from the atmosphere, incorporating the carbon into plant tissues. Normally, when plants die and decompose, this carbon returns to the atmosphere. But in Carboniferous swamps, the carbon was locked away in peat and eventually coal, removed from the active carbon cycle for hundreds of millions of years. Atmospheric carbon dioxide levels plummeted from perhaps 1,500 parts per million in the early Carboniferous to as low as 350 parts per million by the late Carboniferous, close to pre-industrial modern levels. This dramatic drawdown of greenhouse gases caused global cooling, contributing to glaciation in Gondwana. At the same time, the photosynthesis that removed carbon dioxide also released oxygen. With vast forests covering the continents and huge quantities of organic carbon being buried rather than decomposing and consuming oxygen, atmospheric oxygen levels rose to unprecedented heights. Measurements from fossil charcoal, which can only form in the presence of fire, which requires oxygen, suggest atmospheric oxygen reached 30 to 35% during the Pennsylvanian, compared to 21% today. This hyperoxic atmosphere had cascading effects on life, most notably enabling arthropods to reach gigantic sizes. Arthropods breathe through tracheal systems, networks of tubes that deliver air directly to tissues through passive diffusion, rather than active pumping like our lungs. This system works well for small organisms, but becomes less efficient as body size increases because diffusion distance increases. In today's 21% oxygen atmosphere, tracheal breathing limits insects to relatively small sizes. But in the oxygen-rich carboniferous atmosphere, oxygen could diffuse further, allowing arthropods to grow much larger while still meeting their respiratory needs. The result was a world of giant arthropods that would seem nightmarish to modern humans. Arthropleura, a relative of modern millipedes, reached lengths of 2.5 meters and widths of 50 centimeters, about the size of a large dog or small human. It was the largest land arthropod ever to evolve. Fossils suggest it was herbivorous, feeding on plant material and detritus in the forest floor. Meganeura, a dragonfly relative, had a wingspan exceeding 70 centimeters, larger than many modern birds. It was a predator, using huge eyes and agile flight to hunt smaller arthropods. Giant mayflies, millipedes, spiders, and scorpions all reach sizes far exceeding their modern relatives. These gigantic arthropods share the Carboniferous forests with the first reptiles and with amphibians that had diversified since their appearance in the Devonian. Early tetrapods had evolved into numerous forms, some fully aquatic, others terrestrial, still others transitioning between the two. Large predatory amphibians like Crassigyrinus, reaching 2 meters in length, hunted in freshwater pools and swamps. Smaller amphibians inhabited the forest floor, feeding on invertebrates. Most amphibians still required water for reproduction, laying eggs that developed into aquatic larvae with gills before metamorphosing into air-breathing adults. The evolution of the amniotic egg during the Carboniferous represented one of the most important innovations in vertebrate history. Amphibian eggs, like those of fish, must be laid in water or very moist environments because they're enclosed in a simple jelly-like membrane that provides little protection against desiccation. The amniotic egg, by contrast, has a hard or leathery shell and contains specialized membranes, the amnion, chorion, and allantois, that protect the embryo, manage gas exchange, and store waste products. This innovation allowed reptiles to reproduce completely independently of water, opening up terrestrial environments that were too dry for amphibians. The earliest known reptiles appear in the fossil record from the mid-Carboniferous, around 320 million years ago. These were small, lizard-like creatures probably resembling modern lizards in general appearance, though not closely related. Hylonomus, one of the earliest known reptiles, was only about 20 centimeters long and lived in the upright stumps of fossil scale trees, where numerous fossils have been found. Apparently the animals fell in and couldn't escape. Early reptiles were not particularly diverse or abundant during the Carboniferous, but they set the stage for the great reptile radiations that would dominate the Mesozoic era. The Carboniferous coal forests were dynamic ecosystems with complex interactions. Plants competed for light, water, and nutrients. Herbivorous arthropods fed on leaves, stems, and roots, sometimes causing significant damage. Fossilized leaves show insect feeding traces. Predatory arthropods and early tetrapods hunted the herbivores. Decomposers, though less efficient than modern ones, still broke down dead organic matter. Fungi formed symbiotic relationships with plant roots, helping absorb nutrients. The structure of these ecosystems, with multiple trophic levels and complex food webs, resembled modern terrestrial ecosystems in basic organization, even though the species were completely different. Climate during the Carboniferous was complex and changed significantly over the period's 60 million year duration. The early Carboniferous experienced warm, stable conditions globally, with minimal temperature differences between equator and poles. There's no evidence for polar ice caps during this time. However, as atmospheric carbon dioxide declined due to carbon burial in coal swamps and increased chemical weathering enhanced by forest root systems, global temperatures cooled. By the late Carboniferous, glaciers formed on Gondwana, which was positioned over the South Pole. The late Carboniferous glaciation wasn't a single long ice age, but rather a series of glacial advances and retreats controlled by orbital cycles similar to the Milankovitch cycles that drive recent ice ages. When glaciers grew, they locked up water, causing global sea level to fall by as much as 100 meters. When glaciers melted, sea levels rose again. These sea level fluctuations had dramatic effects on the coal swamps, alternately exposing them to allow forest growth and flooding them with marine water. The resulting sedimentary sequences, called cyclothems, show repeated layers of coal, terrestrial sediments, marine limestones, and shales, recording these cycles of glacial advance and retreat. Life on Gondwana, much of which was covered by glaciers or experienced cold climates, differed from the warm equatorial coal forests. Glossopteris, a seed fern that would become dominant in the Permian, was already present in southern regions. The fossil distribution of Glossopteris across South America, Africa, India, Antarctica, and Australia provided some of the earliest evidence that these continents were once connected in the supercontinent Gondwana. Cold-adapted plants and animals evolved in these southern regions, while tropical species dominated equatorial Laurussia and other landmasses. The coal forests began to decline in the latest Carboniferous as climate became drier and more seasonal. The great lycopsid trees, adapted to swampy conditions, couldn't tolerate the increasingly variable moisture levels. They were gradually replaced by seed plants, conifers, and seed ferns that had evolved better adaptations for surviving dry conditions, including deeper root systems, more efficient water transport, and seeds that could remain dormant during unfavorable conditions. This transition from lycopsid-dominated to seed plant-dominated forests accelerated into the subsequent Permian period. The legacy of the Carboniferous forests extends to the present day. The coal deposits formed during this period provide a significant fraction of current global coal reserves. Burning this coal releases the carbon that was removed from the atmosphere 300 million years ago, contributing to modern atmospheric carbon dioxide increases and climate change. The Carboniferous thus provides a dramatic example of how life can alter global chemistry and climate. The forest drew down carbon dioxide and increased oxygen, cooling the planet and enabling giant arthropods, while today's burning of that same ancient plant material is warming the planet and changing atmospheric composition in the opposite direction. The Carboniferous also established terrestrial ecosystems as major global forces. Before this period, marine ecosystems dominated Earth's biology and biogeochemistry. But the vast forests of the Carboniferous, covering extensive areas of the continents, transferred huge amounts of carbon from the atmosphere to the land and eventually to buried deposits. Terrestrial life became a major component of the global carbon cycle, a role it maintains today. The evolution of more complex forest structures with multiple canopy layers created diverse habitats that supported increasingly complex animal communities. By the end of the Carboniferous around 299 million years ago, Earth's continents were approaching the final stages of assembling into the supercontinent Pangaea. Gondwana in the south was colliding with Laurussia in the north, creating the Appalachian Mountains and similar ranges. This continental collision would continue into the Permian, eventually joining virtually all of Earth's landmasses into a single enormous continent stretching from pole to pole. The formation of Pangaea would have profound effects on climate, ocean circulation, and the evolution of life, setting the stage for both the greatest diversification of reptiles and the worst mass extinction in Earth's history. In the long history of mass extinctions, those relatively brief intervals when species disappear at rates far exceeding the background extinction rate, one event stands out as the most catastrophic. It occurred 252 million years ago at the boundary between the Permian and Triassic periods, and it came devastatingly close to ending complex life on Earth entirely. Paleontologists call it the Permian-Triassic extinction event, or simply the Great Dying. In the oceans, an estimated 96% of marine species went extinct. On land, 70% of terrestrial vertebrate species disappeared. Entire ecosystems collapsed, and the recovery took millions of years. Whatever caused this extinction was more devastating than the asteroid impact that killed the dinosaurs, more severe than any other crisis in the fossil record. The Permian period, lasting from 299 to 252 million years ago, began in the aftermath of the Carboniferous coal forests and the ongoing assembly of Pangaea. By the early Permian, nearly all of Earth's continental landmasses had joined into this single supercontinent, the largest in the past 600 million years. Pangaea stretched from the North Pole to the South Pole, surrounded by a single global ocean called Panthalassa. A smaller embayment called the Tethys Sea separated the eastern arm of Pangaea from the main body, but otherwise the continents formed an unbroken landmass. The formation of Pangaea had profound effects on climate and life. With so much land in the continental interior far from oceans, vast regions experienced extremely arid conditions. Coastal areas received moisture from the ocean, but rain-bearing winds lost their moisture before reaching the interior, creating enormous deserts across central Pangaea. These deserts, larger than any modern desert, covered much of what is now western North America, northern Europe, and Central Asia. Sedimentary rocks from the Permian show extensive red beds, oxidized sediments characteristic of arid conditions, and evaporite deposits where ancient lakes and seas evaporated, leaving behind salt and gypsum. Marine life during the Permian recovered from earlier extinction events and developed complex reef ecosystems. However, these reefs weren't built by corals. The reef-building corals familiar today hadn't evolved yet. Instead, Permian reefs were constructed by bryozoans, colonial filter feeders, sponges, and calcareous algae. These reefs supported diverse communities of brachiopods, lamp shells, crinoids, sea lilies, ammonoids, shelled relatives of squid and octopuses, and numerous other invertebrates. Fish, including sharks and bony fish, were abundant and diverse. The oceans appeared healthy and thriving. On land, reptiles diversified dramatically during the Permian, filling ecological niches that had been occupied by amphibians in the Carboniferous. By the Middle Permian, numerous reptile groups had evolved, including ancestors of mammals, turtles, and the lineage leading to dinosaurs. The synapsids, often incorrectly called mammal-like reptiles, though they're actually more closely related to mammals than to reptiles, became particularly diverse and dominant. Early synapsids like Dimetrodon, famous for its dramatic back sail, were apex predators reaching 3 to 4 meters in length. Later synapsids evolved increasingly mammal-like features including differentiated teeth, more efficient jaws, and possibly fur and warm-bloodedness. Herbivorous synapsids like Moschops and Diictodon became abundant, using their specialized teeth to process tough plant material. The evolution of effective herbivory on land required solving challenges that don't face. Plant material is less nutritious than animal tissue and contains tough structural fibers that are difficult to digest. Permian herbivores evolved various strategies including large body sizes to house long digestive systems, batteries of grinding teeth, and possibly gut bacteria to ferment plant material, similar to modern ruminants. As the Permian continued, synapsids evolved increasingly sophisticated features. The therapsids, advanced synapsids that appeared in the Middle Permian, showed numerous characteristics linking them to mammals. Their legs moved more directly under the body rather than sprawling to the sides, allowing more efficient locomotion. Their jaws became more powerful and complex, with differentiated teeth for different functions. Some probably had fur, though this rarely fossilizes. By the late Permian, therapsids dominated terrestrial ecosystems, with species ranging from tiny insectivores to large herbivores and predators. Meanwhile, the ancestors of modern reptiles, the diapsids, were also evolving, though they remained less common than synapsids during the Permian. This group would later give rise to lizards, snakes, crocodilians, dinosaurs, and birds. The stage was set for competition between synapsid and diapsid lineages, a competition that would be dramatically reset by the end-Permian extinction. Around 252 million years ago, Earth's environment underwent rapid and catastrophic changes. The proximate cause appears to have been the largest volcanic eruption in the past 500 million years, the Siberian Traps eruption. In a region covering much of modern Siberia, over 2 million square kilometers, massive flood basalts poured from fissures in the crust. These weren't explosive eruptions like Mount St. Helens, but rather effusive eruptions where lava flowed like water across the landscape, building up layer upon layer to thicknesses exceeding 3 kilometers in some areas. The Siberian Traps eruption was triggered by a mantle plume, a rising column of exceptionally hot rock from deep in Earth's mantle. When this plume reached the surface, it didn't erupt through a single volcano, but rather through countless fissures spread across a vast area. The eruption lasted perhaps 1 to 2 million years, though the most intense phase may have lasted only a few 100,000 years. The volume of lava extruded exceeded 4 million cubic kilometers, enough to cover the entire surface of Earth in a layer 8 meters thick. The environmental consequences were devastating. The eruption released enormous quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. Carbon dioxide built up over the long duration of the eruption, creating an intense greenhouse effect that raised global temperatures by perhaps 8 to 10 degrees Celsius, catastrophic warming on a timescale too rapid for most species to adapt through evolution. Ocean temperatures rose from typical values around 20 degrees Celsius to as high as 40 degrees Celsius in some regions, too hot for most marine life to survive. Sulfur dioxide from the eruption reacted with water vapor in the atmosphere to form sulfuric acid, which fell as acid rain that killed vegetation, acidified soils, and damaged marine ecosystems. In the short term, sulfur aerosols in the stratosphere blocked sunlight, causing temporary global cooling that would have been followed by intense warming as the aerosols settled out but greenhouse gases remained. This rapid climate oscillation, severe cooling followed by extreme warming, would have been particularly deadly, preventing organisms from adapting to stable conditions. The Siberian eruptions also had less obvious but equally deadly effects. The magma passed through thick deposits of limestone, coal, and salt, heating these materials and releasing additional greenhouse gases and toxic compounds. Heating coal deposits released methane and more carbon dioxide. Heating evaporite deposits released chlorine and fluorine compounds that attacked the ozone layer. The combination of direct volcanic gases and gases released from heated sedimentary rocks created a toxic cocktail that poisoned the atmosphere and oceans. Ocean acidification accompanied the warming. As carbon dioxide dissolved in seawater, it formed carbonic acid, lowering ocean pH. The acidification made it difficult for organisms to build calcium carbonate shells and skeletons, affecting everything from microscopic plankton to large-shelled animals. Modern ocean acidification from burning fossil fuels mirrors this ancient event, though so far on a smaller scale. Perhaps most deadly was the development of ocean anoxia, the loss of dissolved oxygen from seawater. Perhaps most deadly was the development of ocean anoxia, the loss of dissolved oxygen from seawater. Warm water holds less dissolved gas than cold water, so as ocean temperatures rose, oxygen levels dropped. Additionally, the warming disrupted ocean circulation patterns. In modern oceans, cold, oxygen-rich water sinks at the poles and flows along the ocean floor toward the equator, ventilating the deep ocean. But in the extreme greenhouse conditions of the Permian, even polar waters became too warm to sink effectively. The deep ocean became stagnant and oxygen depleted, creating what scientists call anoxic or euxinic conditions, water not only devoid of oxygen but rich in toxic hydrogen sulfide. These anoxic waters weren't confined to the depths. Evidence suggests they periodically upwell to the surface, poisoning shallow marine environments, and even releasing hydrogen sulfide gas into the atmosphere. Purple and green sulfur bacteria, which thrive in anoxic conditions and produce hydrogen sulfide as a metabolic byproduct, proliferated in the dying oceans. The hydrogen sulfide they produced would have attacked the ozone layer, allowing deadly ultraviolet radiation to reach Earth's surface and further stressing already devastated ecosystems. The extinction unfolded rapidly by geological standards, perhaps in as little as 60,000 years, though dating uncertainties make the exact duration difficult to determine. Marine ecosystems collapsed first and most severely. Trilobites, which had survived for 270 million years through multiple earlier extinction events, finally disappeared entirely. The diversity of brachiopods, crinoids, and bryozoans crashed. Over 90% of plankton species went extinct, disrupting the base of marine food webs. Coral reefs vanished completely, and reef ecosystems wouldn't recover for millions of years. On land, the extinction was somewhat less severe, but still devastating. The dominant synapsids, including the advanced therapsids that seemed poised to continue diversifying toward mammals, were decimated. Entire families and orders went extinct. Forests collapsed as plants died from acid rain, temperature stress, and possibly insect plagues unleashed by ecosystem disruption. Soil erosion accelerated as vegetation disappeared, leading to massive sediment deposits in river valleys and coastal areas. The fossil record shows a dramatic shift from diverse plant communities to sparse vegetation dominated by fungi, the signature of a dead and decaying world. Some organisms survived by virtue of particular adaptations or luck. Small body size helped, as smaller animals need less food and can shelter in protected microhabitats. The ability to burrow provided refuge from temperature extremes and toxic atmospheric conditions. Aquatic organisms living in freshwater systems may have been partially buffered from ocean acidification and anoxia. Some synapsids survived, particularly small insectivorous species, and would eventually give rise to true mammals in the Triassic. Similarly, some diapsid reptiles survived and would diversify into the dominant groups of the Mesozoic. The recovery from the in-Permian extinction was painfully slow. For millions of years during the early Triassic, ecosystems remained impoverished with low diversity and simple food webs. The coal gap, a 10 million year period when coal deposits essentially stopped forming, indicates that forests failed to recover for an extended period. Marine ecosystems showed similar delays, with reef ecosystems absent for 8 to 10 million years. When reefs finally returned, they were built by different organisms, the scleractinian corals that build modern reefs, rather than the bryozoans and sponges of the Permian. Geochemical evidence preserved in rocks from the Permian-Triassic boundary tells the story of environmental catastrophe. Carbon isotope ratios show dramatic excursions indicating massive releases of carbon into the atmosphere. Sulfur isotopes record ocean anoxia and acidification. Mercury concentrations spike at the boundary, consistent with massive volcanism. The sedimentary record shows erosion, soil loss, and environmental degradation. All these independent lines of evidence point to a world in crisis, pushed beyond the tolerance limits of most living things. The Great Dying serves as a stark reminder that even life's seemingly stable dominance of Earth can be disrupted by sufficiently severe environmental change. It took a combination of factors: massive volcanism, greenhouse warming, ocean acidification, anoxia, acid rain, ozone depletion, and ecosystem collapse to nearly end complex life on Earth. The recovery demonstrated life's resilience, but also showed that resilience has limits and that recovery can take millions of years. The world that emerged from the in-Permian extinction was fundamentally different from what came before, with new groups of organisms filling ecological roles vacated by the extinction's victims. The world that emerged from the Permian extinction was a vastly different place than the one that preceded it. The Triassic period, spanning 252 to 201 million years ago, witnessed Earth's slow recovery from near-total ecosystem collapse and the rise of new groups that would dominate for the next 150 million years. Among these new dominants were the dinosaurs, though they wouldn't achieve their full diversity and ecological importance until the subsequent Jurassic period. The Triassic was a time of experimentation, competition, and evolutionary innovation as life rebuilt itself from the ashes of the Great Dying. The early Triassic, roughly the first 10 million years of the period, remained a difficult time for life. Global temperatures stayed elevated, perhaps 5 to 8 degrees Celsius warmer than modern averages, with extreme temperature fluctuations and continued environmental instability. The supercontinent Pangaea remained intact, creating vast interior deserts and extreme seasonal variations. Vegetation was sparse, dominated by seed ferns, conifers, and ferns rather than the diverse forests of earlier periods. Animal diversity remained low, with ecosystems dominated by just a few species, a pattern called disaster fauna that characterizes post-extinction recovery periods. One of the most successful early Triassic animals was Lystrosaurus, a pig-sized herbivorous synapsid that somehow survived the Permian extinction. Fossils of Lystrosaurus are so abundant in early Triassic rocks worldwide that some paleontologists estimate it comprised 95% of terrestrial vertebrates during this time, an extraordinary dominance reflecting both its adaptability and the lack of competition in devastated ecosystems. Lystrosaurus had a barrel-shaped body, short legs, and a beak-like mouth for cropping vegetation. It may have been semi-aquatic, sheltering in burrows, and was likely relatively tolerant of temperature extremes and poor food quality. As the Triassic progressed, conditions gradually improved and diversity increased. By the Middle Triassic, around 240 million years ago, ecosystems had recovered much of their complexity, though the cast of characters had changed. The synapsids, which had dominated Permian landscapes, were in decline. A few groups of synapsids, particularly the cynodonts, advanced forms with increasingly mammal-like characteristics, persisted and would eventually give rise to true mammals. But synapsids no longer dominated terrestrial ecosystems. That role was being taken over by a different group, the archosaurs. Archosaurs, meaning ruling reptiles, are diapsids characterized by specific skull features including openings in front of the eyes and modified ankle joints. The archosaur lineage split into two branches during the Triassic. One branch, the crocodile line or pseudosuchians, initially dominated and included not just ancestors of modern crocodilians but numerous other forms, some armored herbivores, others swift predators, still others semi-aquatic fish-eaters. The other branch, the bird line or cavametatarsalia, initially remained less common but included the ancestors of dinosaurs and pterosaurs. Early dinosaurs appeared during the Middle Triassic around 240 to 230 million years ago, though the exact timing remains uncertain due to gaps in the fossil record and debates over which fossils represent true dinosaurs versus close relatives. The earliest definitive dinosaurs come from the late Triassic around 230 million years ago from sites in Argentina and Brazil. These early dinosaurs were relatively small. Most were 1 to 2 meters long and bipedal, walking on their hind legs with their tails held out for balance. They were carnivorous or omnivorous, hunting smaller animals or scavenging. Heterosaurus, from Argentina's Esquigualasto Formation, dated to about 230 million years ago, represents one of the earliest well-known dinosaurs. At 3 to 6 meters long, it was one of the larger predators of its time, with powerful jaws full of serrated teeth, grasping hands with sharp claws, and long hind legs for running. Heterosaurus and its relatives were early members of the Saurischian lizard-hipped dinosaurs, one of the two major dinosaur groups. The other major group, Ornithischians, bird-hipped, focused on herbivory and would later include iconic dinosaurs like Triceratops and Stegosaurus, though they remained rare in the Triassic. For most of the late Triassic, dinosaurs remained relatively uncommon members of terrestrial faunas, overshadowed by other archosaurs and by various large synapsids and other reptiles. The dominant large herbivores were not dinosaurs but rather rhynchosaurs, pig-sized reptiles with beak-like jaws for cropping vegetation, and various synapsids. The dominant predators included Rauisuchians, large pseudosuchian archosaurs reaching 6 meters in length with powerful jaws and sometimes elaborate armor. These creatures occupied the ecological roles that dinosaurs would later fill. And there's no obvious reason from the Middle to late Triassic fossil record why dinosaurs, rather than these other groups, would eventually dominate. The key to dinosaur success may have lain in subtle advantages that only became significant during another period of environmental crisis. Dinosaurs had evolved an upright posture, with legs positioned directly underneath the body rather than sprawling to the sides. This allowed more efficient locomotion, particularly for sustained activity. Many dinosaurs were probably warm-blooded or at least had elevated metabolic rates compared to typical reptiles, giving them advantages in activity levels, growth rates, and possibly tolerance of temperature fluctuations. These features might not have been decisive under stable conditions, But during times of environmental stress, they could make the difference between survival and extinction. That stress arrived at the end of the Triassic 201 million years ago, in the form of another mass extinction, the Triassic-Jurassic extinction event. While not as severe as the Permian catastrophe, this extinction eliminated approximately 75% of species and dramatically restructured terrestrial and marine ecosystems. The cause, like the Permian event, appears to have been massive flood basalt volcanism, this time the Central Atlantic Magmatic Province, CAMP, associated with the rifting of Pangaea as the Atlantic Ocean began to open. The CAMP eruptions released enormous volumes of lava and volcanic gases, triggering global warming, ocean acidification, and environmental stress similar to but less severe than the Permian event. In the oceans, many groups of marine reptiles, ammonoids, and other organisms went extinct. On land, many of the dominant large animals disappeared. The rhynchosaurs vanished. The Rauisuchians went extinct. Most large synapsids disappeared. Large crocodilian relatives that had dominated terrestrial ecosystems were eliminated. But dinosaurs, for reasons not entirely clear, survived with relatively minor losses and emerged from the extinction as the dominant terrestrial vertebrates. The Jurassic period that followed the extinction, lasting from 201 to 145 million years ago, would witness the true age of dinosaurs. But already in the latest Triassic and earliest Jurassic, dinosaur diversity was increasing. The first large herbivorous dinosaurs appeared, prosauropods like Plateosaurus reaching 5 to 10 meters in length, able to rear up on their hind legs to reach high vegetation. These early giants were the precursors to the truly enormous sauropods that would dominate Jurassic landscapes. Early theropods, the group of carnivorous dinosaurs that includes famous predators like Tyrannosaurus rex, diversified into various sizes and hunting strategies. Coelophysis, a lightly built theropod from the late Triassic of New Mexico, reached 3 meters in length and hunted in packs, as evidenced by mass death assemblages containing hundreds of individuals. The evolution of pack hunting behavior suggests sophisticated social interactions and coordination. The Triassic also witnessed the origin and early evolution of pterosaurs, the flying reptiles that would dominate Mesozoic skies. Early pterosaurs like Eudomorphodon appeared in the late Triassic with wingspans of about a meter. They had long tails, numerous teeth, and wings formed by membranes stretching from extremely elongated fourth fingers to the body and legs. These creatures weren't birds. Birds wouldn't evolve until the Jurassic from small theropod dinosaurs, but they occupied similar ecological roles as aerial insectivores and fish eaters. Another important group that appeared during the Triassic was the true mammals. These evolved from cynodont synapsids, the most advanced mammal-like synapsids of the late Triassic. The transition from cynodonts to mammals involved numerous gradual changes in skull structure, jaw mechanics, teeth, hearing apparatus, and almost certainly metabolism and reproduction. The earliest true mammals, appearing around 210 to 200 million years ago, were tiny creatures. Most were mouse-sized or smaller, with specialized teeth for eating insects and other small prey. Mammals evolved several key innovations during their cynodont to mammal transition. The lower jaw simplified from multiple bones to a single bone, the dentary, while the other jaw bones migrated to the middle ear where they evolved into the tiny bones that transmit sound vibrations, an example of evolutionary repurposing of existing structures. Mammals developed highly differentiated teeth, incisors, canines, premolars, and molars, allowing efficient processing of different foods. They evolved fur for insulation and likely warm-bloodedness, maintaining constant high body temperatures independent of environmental conditions. Most revolutionary, they evolved milk production and extended parental care, allowing better survival of offspring. Despite these innovations, Triassic and early Jurassic mammals remained small, nocturnal insectivores, constrained to ecological niches that didn't compete directly with dinosaurs. Mammals would remain relatively small and inconspicuous for the next 140 million years, throughout the age of dinosaurs, only diversifying into larger forms after non-avian dinosaurs went extinct at the end of the Cretaceous. The late Triassic world looked very different from earlier periods. Pangaea remained largely intact but was beginning to rift apart, with early stages of the Atlantic Ocean opening between what would become North America and Africa. Climate remained warm and relatively arid in continental interiors, though gradually becoming more humid. Vegetation included conifers, seed ferns, cycads, ginkgos, and ferns, creating forests quite different from earlier coal swamp forests or later flowering plant-dominated ecosystems. In the oceans, recovery from the Triassic-Jurassic extinction was underway. Scleractinian corals, which had first appeared in the Middle Triassic, began building reefs again after the extinction. These are the same group that builds modern coral reefs. Marine reptiles diversified, including ichthyosaurs, streamlined, dolphin-like reptiles, plesiosaurs, long-necked fish-eaters, and early crocodilian relatives. Fish continue diversifying, with modern groups of bony fish and sharks becoming increasingly abundant. The Triassic period represents a crucial transitional time in Earth's history between the ancient Paleozoic world dominated by synapsids, amphibians, and primitive reptiles, and the Mesozoic world of dinosaurs, pterosaurs, marine reptiles, and early mammals. The environmental upheavals of the in-Permian and in-Triassic extinctions reshuffled the ecological deck, eliminating dominant groups and giving opportunities to survivors. The dinosaurs, pterosaurs, and other archosaurs that survived the in-Triassic extinction would go on to dominate terrestrial and aerial ecosystems for the next 135 million years. The reasons for dinosaur success remain debated among paleontologists. Was it superior adaptations, better locomotion, higher metabolism, more efficient respiration? Was it competitive superiority, outcompeting other groups for food and habitat? Or was it simply luck, surviving extinction events that eliminated competitors? The answer probably involves all these factors. Dinosaurs possessed genuine adaptive advantages, but they also benefited from extinction events that removed competitors and opened ecological opportunities. By the end of the Triassic, 201 million years ago, the stage was set for the Mesozoic era's full flowering. Pangaea was breaking apart, creating new ocean basins and altering climate patterns. Dinosaurs had survived the in-Triassic extinction and were positioned to diversify and dominate. Pterosaurs ruled the skies. Marine reptiles controlled the oceans. Mammals existed but remained small and inconspicuous. The climate was warm, vegetation was abundant in many regions, and atmospheric oxygen had recovered to near-modern levels. The age of dinosaurs was about to begin in earnest. The evolutionary experiments of the Triassic established patterns that would persist throughout the rest of the Mesozoic. Archosaurs dominated large-bodied terrestrial niches. Mammals remained small, nocturnal, and specialized for eating insects and other small prey. Crocodilians transitioned to semi-aquatic lifestyles where they remain today. Turtles, which had appeared in the late Triassic, continued their conservative body plan that has persisted with little change for over 200 million years. The basic structure of Mesozoic ecosystems was in place. The Triassic also demonstrates life's remarkable resilience in the face of catastrophe. The in-Permian extinction had come close to ending complex life entirely, yet within 50 million years, less than 2% of Earth's history, ecosystems had not only recovered but had generated entirely new forms more diverse and in some ways more sophisticated. Then what came before? Evolution didn't simply replace what was lost. It innovated, creating fundamentally new body plans and ecological strategies. The dinosaurs and mammals that emerged from the Triassic would shape the next 200 million years of Earth's history and ultimately give rise to the modern world. As the Triassic gave way to the Jurassic, Earth was entering what many consider the classic age of dinosaurs, a time when these remarkable reptiles would evolve into forms ranging from chicken-sized predators to the largest land animals ever to walk the Earth, when forests of conifers and cycads would carpet the continents, and when the planet's geography would be fundamentally reshaped by the breakup of Pangaea and the opening of new ocean basins. The foundation laid in the Triassic would support the magnificent edifice of Jurassic and Cretaceous life. The Jurassic and Cretaceous periods, spanning from 201 to 66 million years ago, represent the full flowering of the dinosaur age, 135 million years during which these remarkable reptiles dominated terrestrial ecosystems across every continent. This was the era of giants, when herbivorous sauropods weighing 50 to 80 tons browsed on treetop vegetation, when armored stegosaurs and ankylosaurs defended themselves with spikes and clubs, and when predators like Allosaurus and eventually Tyrannosaurus rex hunted with devastating efficiency. But the Mesozoic wasn't just about dinosaurs. The skies filled with pterosaurs ranging from sparrow-sized insect hunters to creatures with wingspans exceeding 10 meters. The oceans teemed with marine reptiles, enormous fish, and the ancestors of modern sharks. Plants evolved flowers, transforming terrestrial landscapes and food webs. Mammals persist in the shadows, slowly diversifying while remaining small. And the continents themselves were on the move, as Pangaea broke apart and modern ocean basins opened. The Jurassic period, from 201 to 145 million years ago, saw dinosaurs truly come into their own. After surviving the end-Triassic extinction, dinosaurs diversified rapidly, filling ecological niches vacated by extinct competitors. By the Middle Jurassic, around 170 million years ago, dinosaur faunas had developed remarkable diversity and specialization. The sauropods, the long-necked, long-tailed herbivores, evolved into the largest land animals ever to exist. Brachiosaurus, despite being one of the better-known sauropods, wasn't even the largest, reaching only about 25 meters in length and perhaps 40 tons. Diplodocus stretched even longer at up to 35 meters but was more lightly built, with much of its length in its extraordinarily long neck and whip-like tail. How could land animals grow so large? Sauropods evolved numerous adaptations that made their enormous size possible. Unlike mammals, which are limited by the energy required to maintain constant body temperature, dinosaurs likely had intermediate metabolic rates between typical reptiles and mammals, reducing energy costs while maintaining reasonably high activity levels. Their bones were extensively pneumatized, filled with air spaces connected to the respiratory system, reducing weight while maintaining strength. Their long necks allowed them to reach a huge feeding radius without moving their massive bodies, minimizing energy expenditure while maximizing food intake. Sauropods also had highly efficient respiratory systems involving air sacs similar to those in modern birds. Air flowed in one direction through the lungs rather than in and out like in mammals, allowing for more complete oxygen extraction. This efficient respiration would have been crucial for supplying oxygen to their enormous bodies. Additionally, sauropods laid eggs rather than giving live birth, avoiding the metabolic costs and physical constraints of pregnancy that limit maximum size in mammals. A female blue whale, the largest animal ever, carries a single fetus for about a year. A sauropod could lay dozens of eggs, each developing externally, allowing reproduction without size constraints. The herbivorous diet of sauropods required processing enormous quantities of vegetation daily, perhaps 200 to 400 kilograms or more for the largest species. Unlike modern ruminants, sauropods didn't chew their food extensively. Instead, they cropped vegetation with peg-like teeth, swallowed it whole, and relied on gastroliths, swallowed stones in the stomach that acted like a mill to grind plant material, and probably gut bacteria to break down tough plant fibers. Their extremely long intestines provided ample time and space for microbial fermentation to extract nutrients from plant matter. Carnivorous theropod dinosaurs evolved to hunt these giants, though most theropods were considerably smaller than their prey. Allosaurus, the apex predator of the late Jurassic around 150 million years ago, reached 8 to 10 meters in length and perhaps a ton or more in weight, large, but tiny compared to sauropods weighing 20 to 50 times more. Allosaurus and other large theropods probably hunted in packs or focused on juvenile sauropods, using slashing bites to wound and weaken prey before moving in for the kill. Their serrated teeth, constantly replaced throughout life, acted like steak knives, slicing through flesh. Other Jurassic dinosaurs showed remarkable adaptations for defense and feeding. Stegosaurus, instantly recognizable from its distinctive back plates and tail spikes, was a medium-sized herbivore reaching about 9 meters in length. The function of its plates has been debated. Possibilities include defense, display, or thermoregulation, with the latter two most likely given that the plates were covered in skin rich in blood vessels. The tail spikes, called a thagomizer, a term coined by cartoonist Gary Larson and adopted by paleontologists, were clearly defensive weapons and fossil evidence of Allosaurus bones with puncture wounds matching Stegosaurus tail spikes confirms they were used in combat. Smaller dinosaurs filled various ecological niches. Ornithopods, bipedal herbivores, ranged from tiny forms the size of chickens to multi-ton giants. Many had specialized teeth and jaws for processing tough vegetation, and some could switch between bipedal and quadrupedal locomotion. Small theropods like Compsognathus, about the size of a turkey, hunted insects, small reptiles, and early mammals. These small predators were likely the most abundant dinosaurs by number of individuals, though large dinosaurs dominated in terms of biomass. A revolutionary discovery in recent decades has been the abundance of feathers among theropod dinosaurs. For many years, paleontologists assumed dinosaurs had scales like modern reptiles. But fossils from China's Liaoning province, discovered starting in the 1990s, preserve extraordinary details including feathers, fur, and soft tissues. These fossils reveal that many theropods, from small species to even some large tyrannosaurs, bore feathers. Early feathers were simple filaments used for insulation, but more derived theropods evolved complex feathers with veins and barbs like modern bird feathers, used for display and eventually for flight. Birds evolved during the late Jurassic from small feathered theropods. Archaeopteryx, from about 150 million years ago in Germany, represents a transitional form between non-avian dinosaurs and modern birds. It had feathers and wings capable of flight, but also retained teeth, claws on its wings, and a long bony tail, features lost in later bird evolution. Whether Archaeopteryx could fly-powered flight or was limited to gliding remains debated, but it clearly represents an early experiment in avian flight. Birds would diversify throughout the Cretaceous, though modern bird groups wouldn't appear until after the end Cretaceous extinction. Pterosaurs continued to dominate Mesozoic skies alongside early birds. Jurassic pterosaurs like Pterodactylus were relatively small with wingspans around a meter, but later Cretaceous pterosaurs would grow to enormous sizes. Pteranodon had wingspans of 6 to 7 meters, while Quetzalcoatlus, one of the largest flying animals ever, had wingspans exceeding 10 meters, as large as small aircraft. These giants were likely capable soarers, using thermal updrafts to stay aloft while expending minimal energy, hunting fish or small terrestrial animals. The Cretaceous period, from 145 to 66 million years ago, was the final and longest period of the Mesozoic era. It witnessed continued dinosaur diversification and the emergence of many iconic species. The early and middle Cretaceous saw the rise of new herbivore groups, including the ornithopod hadrosaurs or duck-billed dinosaurs, which would become extraordinarily diverse and abundant in the late Cretaceous. Iguanodon, one of the first dinosaurs ever discovered and described scientifically in the 1820s, was an early relative of hadrosaurs reaching 10 meters in length with distinctive thumb spikes possibly used for defense or food gathering. The Cretaceous also witnessed the evolution of the ceratopsians, the horned dinosaurs, and ankylosaurs, the armored tanks of the dinosaur world. Early ceratopsians were relatively small with minimal horns or frills, but they would evolve into giants like Triceratops by the late Cretaceous. Triceratops reached 9 meters in length with a massive skull, featuring 3 horns and a huge bony frill. These were likely social animals living in herds for defense against predators, using their horns in intraspecific combat and defense. Ankylosaurs evolved heavy armor consisting of bony plates embedded in the skin, some with massive tail clubs capable of delivering devastating blows. Ankylosaurus, the largest and last of the ankylosaurs, reached 8 meters in length and weighed perhaps 6 tons, covered in armor that would have made it nearly invulnerable to predators. The tail club, formed from fused vertebrae and covered in bony plates, could generate tremendous force, potentially capable of breaking the leg bones of attacking theropods. The apex predators of the Cretaceous included some of the most famous dinosaurs. Tyrannosaurus rex, from the very end of the Cretaceous around 68 to 66 million years ago, reached 12 to 13 meters in length and 8 to 9 tons in weight, one of the largest terrestrial predators ever. Its massive skull, up to 1.5 meters long, housed huge banana-sized teeth capable of crushing bone. Bite force estimates suggest T-Rex could exert over 12,000 pounds of force, stronger than any land predator before or since. Recent research suggests T-Rex had exceptional vision, keen sense of smell, and possibly sophisticated pack-hunting behaviors, making it a formidable apex predator. The Cretaceous world was transformed by one of the most important innovations in plant evolution, flowering plants or angiosperms. These appeared in the fossil record around 130 million years ago and diversified explosively, becoming dominant in many ecosystems by the late Cretaceous. Flowering plants had numerous advantages over earlier seed plants like conifers and cycads. Flowers enabled more efficient pollination through partnerships with insects and other animals. Fruits evolved to enclose seeds and attract animals that would disperse them. Deciduous leaves that could be shed allowed plants to conserve water and nutrients. Faster growth rates enabled rapid colonization of disturbed areas. The rise of flowering plants transformed terrestrial ecosystems and coevolution with pollinators and seed dispersers. Bees, butterflies, and other pollinating insects diversified alongside flowers. Fruits and seeds provided new food sources for dinosaurs, mammals, and birds. Forests shifted from conifer-dominated to include abundant flowering trees. Grasslands, though not yet widespread, began appearing by the late Cretaceous. The coevolution of plants and animals created more complex and interconnected food webs than had existed earlier in the Mesozoic. Geographic changes during the Jurassic and Cretaceous were equally dramatic. Pangaea continued breaking apart throughout this time. The central Atlantic Ocean widened between North America and Africa. The South Atlantic began opening between South America and Africa around 130 million years ago. By the mid-Cretaceous, sea levels had risen to their highest points in Earth's history, flooding low-lying continental areas and creating vast inland seas. The western interior seaway divided North America from north to south, connecting the Arctic Ocean to the Gulf of Mexico and creating two separate landmasses, Laramidia in the west and Appalachia in the east. These inland seas and continental separations created isolated landmasses where dinosaur populations evolved independently, generating high diversity. Laramidian dinosaurs differed from Appalachian forms. Asian dinosaurs differed from North American species. The fossil record shows geographic variation and endemism, species restricted to particular regions, indicating that ocean barriers prevented widespread dispersal even for animals as large and mobile as dinosaurs. Marine life during the Jurassic and Cretaceous was equally diverse. Marine reptiles including ichthyosaurs, plesiosaurs, and mosasaurs filled ecological roles similar to modern whales, dolphins, and seals. Ichthyosaurs were streamlined, dolphin-like reptiles that gave live birth at sea and fed primarily on fish and squid. Plesiosaurs included long-necked forms that used their necks like fishing rods to catch prey, and short-necked pliosaurs with massive skulls and teeth that hunted large prey, including other marine reptiles. Mosasaurs, which appeared in the mid-Cretaceous and diversified rapidly, were large marine lizards reaching 15 meters or more, the apex predators of late Cretaceous seas. Fish continue diversifying, with modern groups of bony fish and sharks becoming increasingly abundant and varied. Ammonites, shelled cephalopods related to modern nautilus, were extraordinarily diverse with thousands of species, though they would go extinct at the end of the Cretaceous. Belemnites, relatives of modern squid, were common. Marine ecosystems supported complex food webs from microscopic plankton through various levels of predators. Climate during the Jurassic and Cretaceous was generally warmer than today, with no polar ice caps for most of this time. Dinosaur fossils from near the poles suggest forests extended to high latitudes, though these areas experienced months of winter darkness that would have challenged life. Some dinosaurs may have been capable of surviving Arctic conditions through insulation, feathers or fat, hibernation, or seasonal migration. The warm climate was sustained by high atmospheric carbon dioxide levels from volcanic activity, particularly during the Cretaceous when volcanic activity was exceptionally intense. The Mesozoic saw mammals persisting and slowly diversifying, though they remained small and mostly nocturnal. Early mammals evolved into several groups including monotremes, egg-laying mammals, ancestors of modern platypus and echidnas, multituberculates, rodent-like omnivores that would be successful through the Mesozoic and into the Paleogene, and various groups of marsupials and placentals that would later dominate after dinosaur extinction. These mammals filled ecological niches as insectivores, small omnivores, and possibly some as aquatic forms, but none evolved to large sizes or competed directly with dinosaurs for dominance. By the late Cretaceous, around 70 to 66 million years ago, dinosaur diversity was at or near its peak. Dozens of species coexisted in some regions, filling every available ecological niche from tiny insectivores to massive herbivores and fearsome predators. Complex ecosystems with multiple trophic levels, sophisticated predator-prey relationships, and intricate plant-animal interactions characterized the end-Cretaceous world. Life seemed secure in its Mesozoic patterns. But the stage was being set for catastrophe. An asteroid was approaching Earth on a collision course that would end the reign of the dinosaurs and open the way for mammals, including eventually humans, to inherit the planet. On a day 66 million years ago, the sky over what is now Mexico's Yucatan Peninsula suddenly lit up brighter than 1,000 suns. An asteroid roughly 10 kilometers in diameter, traveling at over 20 kilometers per second, more than 40,000 miles per hour, struck the Earth with the force of billions of nuclear weapons detonating simultaneously. The impact excavated a crater 180 kilometers across and 20 kilometers deep in seconds, vaporizing the asteroid and vast quantities of rock, sending a fireball, expanding outward at supersonic speeds. The energy released exceeded 10 billion times that of the atomic bombs dropped on Hiroshima and Nagasaki. In that single moment, the fate of life on Earth changed forever. The age of dinosaurs was ending, and the age of mammals was about to begin. The evidence for this impact is overwhelming and comes from multiple independent lines of investigation. In 1980, physicist Luis Alvarez and his geologist son Walter Alvarez published a revolutionary paper proposing that an asteroid impact caused the extinction of the dinosaurs. They based this on a thin layer of clay found at the Cretaceous-Paleogene boundary, the KPG boundary, formerly called KT boundary, at sites around the world. This clay layer, typically just a few centimeters thick, contained extraordinarily high concentrations of iridium, a metal rare in Earth's crust but common in asteroids and comets. The iridium anomaly suggested that an enormous asteroid had struck Earth, vaporizing and spreading its material globally as dust that eventually settled out of the atmosphere. Critics initially doubted the hypothesis, suggesting volcanic eruptions or other causes for the iridium layer. But subsequent discoveries provided overwhelming support. Shocked quartz grains showing distinctive fracture patterns only produced by extreme pressure, was found at the KPG boundary, indicating violent impacts. Tiny spherules of molten rock that had been ejected into the atmosphere and rained back down were discovered. Soot from global wildfires appeared in the boundary layer. The smoking gun came in 1991 when geologists identified the Chicxulub crater, buried beneath sediments on Mexico's Yucatan Peninsula. The crater, revealed through gravitational and magnetic surveys, is exactly 66 million years old, precisely matching the KPG boundary. Drilling into the crater has recovered rocks showing definitive evidence of impact, melted and shocked minerals, mixed materials from different depths, and devastation patterns consistent with asteroid collision. The Chicxulub impact site leaves no doubt that a massive asteroid struck Earth at exactly the time when dinosaurs and many other organisms went extinct. The immediate effects of the impact were catastrophic beyond imagination. The asteroid struck in shallow seas, vaporizing water and sedimentary rocks rich in sulfur and carbon. The impact generated magnitude 10 to 11 earthquakes, far stronger than any in human history, that would have been felt globally. Tsunamis hundreds of meters high radiated outward from the impact site, devastating coastlines across the Gulf of Mexico and Caribbean. Some tsunami deposits have been found as far inland as Texas and Alabama, containing jumbled masses of rock, fossils, and debris swept inland by the waves. The fireball from the impact expanded outward, heating the atmosphere to thousands of degrees over a vast area. This thermal pulse ignited wildfires across North America and possibly globally. Debris ejected from the crater re-entered the atmosphere around the world, heating the air through friction to temperatures that could ignite plant material. Evidence of extensive wildfires at the KPG boundary includes widespread soot, charcoal, and burned plant material found at sites on multiple continents. Much of Earth's vegetation may have burned within hours to days of the impact. Perhaps most deadly were the longer-term effects. The impact ejected trillions of tons of pulverized rock, soot, and sulfur aerosols into the stratosphere, where they spread globally over weeks to months. This debris cloud blocked sunlight, plunging Earth into darkness and cold in what's termed impact winter. Photosynthesis stopped or was severely reduced. Surface temperatures plummeted, perhaps dropping 20 to 30 degrees Celsius within weeks. This cold snap lasted months to years depending on location, destroying plants and collapsing food webs that depended on primary productivity. The sulfur aerosols from vaporized sedimentary rocks had additional effects. Sulfur dioxide reacted with water vapor to form sulfuric acid, which fell as intense acid rain that acidified soils and surface waters, making them toxic to many organisms. In the oceans, the combination of blocked sunlight, cooling temperatures, and acidification devastated marine ecosystems. Phytoplankton, microscopic photosynthetic organisms forming the base of marine food webs, died off massively. This triggered cascading extinctions up the food chain as herbivores starved, then predators, then top predators and scavengers. The extinction was selective in ways that make sense given the environmental changes. Large animals that required substantial food intake suffered most. Non-avian dinosaurs, with their high metabolism and food requirements, couldn't survive the collapse of plant productivity. Large marine reptiles like mosasaurs and plesiosaurs went extinct. Pterosaurs disappeared entirely. But small animals that could survive on seeds, insects, carrion, or that could hibernate through the worst conditions had better chances. Small mammals, with their burrows providing insulation and their ability to feed on diverse foods, including insects and seeds, survived. Birds, descended from small theropod dinosaurs, mostly survived, though many groups went extinct. In the oceans, extinction was similarly selective. Organisms dependent on photosynthetic plankton suffered catastrophic losses. Ammonites, which had dominated Mesozoic seas for 150 million years, went completely extinct. Many fish groups died out. But organisms that fed on detritus, or that lived in deep-sea environments less dependent on surface productivity, fared better. Sharks and rays survived with some losses. Deep-sea fish persisted. Bottom-dwelling organisms that fed on organic debris weathered the crisis better than surface dwellers. On land, the fossil record shows clear evidence of the extinction severity. Dinosaur fossils are abundant in rocks just below the KPG boundary, then disappear completely from rocks above it, with the exception of birds, which are technically dinosaurs. The boundary itself often contains a fern spike, a layer rich in fern spores but poor in other plant fossils. This suggests that after the extinction, ferns colonized devastated landscapes much as they colonized disturbed areas today, before more diverse plant communities recovered. The sudden dominance of ferns indicates widespread destruction of existing vegetation, followed by gradual recovery. The extinction wasn't instantaneous. Different regions may have experienced different timescales of ecological collapse. Some organisms may have survived weeks or months after the impact before succumbing to starvation or environmental stress. But on geological timescales, the extinction was effectively instantaneous, occurring in perhaps 10,000 years or less, possibly much faster. The transition from thriving Cretaceous ecosystems to devastated post-impact landscapes, then gradual Paleogene recovery, is preserved in sedimentary sequences at sites worldwide. The role of volcanism in the extinction remains debated. The Deccan Traps in India, one of Earth's largest volcanic provinces, erupted massive quantities of lava precisely around the KPG boundary, though dating uncertainties make it unclear whether the most intense eruptions preceded, coincided with, or followed the impact. Some scientists argue that Deccan volcanism was already stressing ecosystems, making them more vulnerable to the impact, while others suggest the impact's seismic energy may have triggered intensified volcanic activity. The consensus view is that the asteroid impact was the primary extinction driver, though volcanism may have contributed. Recovery from the extinction took millions of years and unfolded in stages. The first communities to re-establish were simple, low-diversity assemblages of opportunistic species that could tolerate disturbed conditions. Ferns dominated early plant communities. Small generalist mammals survived by feeding on seeds, insects, and organic debris. As climate stabilized and plant productivity recovered, ecosystems gradually increased in complexity. New plant communities emerged, different from Cretaceous forests. Mammals began diversifying into vacant ecological niches left by dinosaur extinction. By about 10 million years after the impact, early Paleogene ecosystems had recovered much of their complexity, though with a completely different cast of characters. Mammals had begun diversifying into larger forms, filling herbivore and predator roles once occupied by dinosaurs. Early ungulates, hoofed herbivores ancestral to modern horses, cattle, and elephants, appeared. Early primates, the group that would eventually lead to humans, emerged. Carnivorous mammals evolved, initially small but gradually increasing in size to fill apex predator roles. Birds diversified rapidly in the aftermath, taking advantage of ecological opportunities left by pterosaur extinction and the opening of new niches as forests recovered. Modern bird groups, including waterfowl, shorebirds, parrots, and songbirds, appeared during the Paleogene. Birds evolved diverse body forms and ecological strategies, from tiny hummingbirds to large flightless forms to seabirds covering vast ocean distances. The Cenozoic era that followed the KPG extinction, the era of recent life spanning 66 million years ago to the present, would witness the diversification of mammals into the dominant terrestrial vertebrates. The mammals that survived the extinction were small, mostly mouse-sized to rat-sized insectivores and omnivores. But within 10 to 20 million years, mammals had diversified into forms ranging from tiny shrews to elephant-sized herbivores. By 40 million years ago, many modern mammal groups had appeared, including bats, whales, primates, rodents, carnivores, and various herbivore groups. The evolution of whales from terrestrial ancestors represents one of the most dramatic evolutionary transitions. Around 50 million years ago, four-legged land mammals related to hoofed ungulates began adapting to aquatic lifestyles, initially in rivers and coastal waters. Over 10 to 15 million years, they evolved increasingly specialized adaptations for marine life, limbs modified into flippers, tails evolving into flukes for propulsion, nostrils moving to the top of the head to form blowholes, and bodies becoming streamlined. By 35 million years ago, fully aquatic whales resembling modern forms had evolved, filling ecological roles left vacant by marine reptile extinction. Primates, the group that includes lemurs, monkeys, apes, and humans, appear by about 55 million years ago as small, tree-dwelling insectivores and fruit-eaters. They evolved grasping hands, forward-facing eyes providing depth perception, and larger brains relative to body size compared to most mammals. These adaptations for arboreal life would later prove advantageous for tool use and complex cognition. By 25 to 30 million years ago, primates had split into several major groups. The lineage leading to African apes and humans diverged from other primates around 25 million years ago. Flowering plants continued dominating terrestrial ecosystems and diversifying throughout the Cenozoic. Grasslands expanded dramatically starting around 30 to 40 million years ago, driven by climate changes that favored drought-tolerant grasses over forests in many regions. These grasslands supported new mammal adaptations, grazing herbivores with specialized teeth for processing tough grass, and predators adapted for hunting on open plains. The coevolution of grasses and grazers shaped many modern ecosystems from African savannas to North American prairies. Climate during the Cenozoic fluctuated dramatically. The early Cenozoic was very warm, warmer than today, with forests extending to polar regions and crocodilians living in what is now the Arctic. Around 50 million years ago began a long-term cooling trend driven by declining atmospheric carbon dioxide and changing ocean circulation patterns. By 34 million years ago, the Antarctic ice sheet had formed. By 2.6 million years ago, the ice ages had begun, with repeated cycles of glacial advances and retreats that continue today. The human lineage emerged within this context of climate change and mammal diversification. Around 7 to 6 million years ago in Africa, the lineage leading to chimpanzees and humans diverged. Early hominins began walking upright, an adaptation possibly related to changing habitats as forests gave way to more open woodlands. By 2 to 3 million years ago, the genus Homo had appeared with larger brains and the beginnings of stone tool use. Homo sapiens, modern humans, evolved around 300,000 years ago in Africa and began spreading globally around 100,000 to 70,000 years ago. The KPG extinction that ended the age of dinosaurs was thus ultimately responsible for human evolution. If the asteroid had missed Earth or struck somewhere else with less devastating effect, dinosaurs might still dominate terrestrial ecosystems. Mammals might have remained small and relatively inconspicuous. The evolutionary path that led from small Cretaceous mammals to modern humans would never have occurred. The asteroid impact was catastrophic for organisms living 66 million years ago, but it created opportunities that ultimately shaped the modern world. The story of the KPG extinction and mammal rise illustrates how evolution works, not through predictable progress toward particular goals, but through organisms adapting to conditions and taking advantage of opportunities, with mass extinctions periodically reshuffling the deck and opening new possibilities. The dinosaurs weren't inferior to mammals. They dominated successfully for 135 million years, far longer than mammals have been dominant. Their extinction resulted from bad luck, being the large animals present when a catastrophic impact occurred, rather than evolutionary inadequacy. Looking back across Earth's prehistoric expanse, from its violent birth 4.6 billion years ago through the origin of life, the oxygenation of the atmosphere, the colonization of land, the age of dinosaurs, and ultimately to the rise of mammals and humans, we see a planet in constant transformation. Continents drift, climates shift, and life evolves in response to challenges and opportunities. Mass extinctions punctuate this story, terrible in their immediate effects, but creative in opening possibilities for survivors. Each chapter of Earth's history sets the stage for the next, with earlier innovations enabling later developments. The prehistoric Earth laid the foundations for everything we see today. The oxygen we breathe was generated by ancient cyanobacteria. The coal and oil we burn represent buried forests and marine organisms from hundreds of millions of years ago. The continents we inhabit have been shaped by billions of years of plate tectonics. The animals and plants around us descended from survivors of multiple mass extinctions. Even our own bodies preserve traces of this deep history. Our inner ear bones derive from reptilian jawbones, our DNA sharing sequences with bacteria, our embryonic development recapitulating aspects of evolutionary history. As we face modern challenges including climate change, habitat destruction, and possible ongoing mass extinction, Earth's prehistoric past provides context and lessons. It shows that climate can change dramatically, with severe consequences for life. It demonstrates that extinction is forever. Species lost cannot be recovered. It reveals that recovery from major disruptions takes millions of years. But it also shows life's remarkable resilience, its ability to adapt, persist, and ultimately flourish even after near-total catastrophe. The story of prehistoric Earth is ultimately our story, the long journey from primordial chemicals to conscious beings capable of understanding our own origins. It's a story still being written as scientists make new discoveries, revise interpretations, and piece together Earth's deep history from the rocks, fossils, and chemistry that preserve its secrets. Every fossil found, every rock analyzed, every isotope measured adds another detail to our understanding of the greatest story ever told, the 4.6 billion year biography of our planet and the life it sustains.